Test. I guess now you can
Are
hear
we
me better.
working?
No? Yeah.
Mic check. Here we go.
And as you can see in the program list, there'll be 2 breaks in the middle. So we would request if you would not bring any food or drinks into the theatre during and after the breaks, please.
And lastly, if you're on Twitter, follow us at TEDx Surrey, and you can tweet us at #TEDx Surrey University. That's basically it for the formalities, and let's get to it.
Yes, that's right. So today we are running a salon event, which basically means it's a much more informal event designed to give you, the audience, a chance to engage with the speakers. So this is how it's going to work. Each speaker will be followed by a TED video, after which there will be a Q&A session where you can ask any questions you have.
So let's get to the speakers. First up is Maya Elliot, who is a 4th-year molecular cell biology student at the University of York. She's half Dutch, and her favourite thing to do is talk to people about science and connect with people through science. This, among other things, led to her entering the FameLab competition, which is a science communication competition in Benelux, where she won the audience prize at the national final. So today, her talk will be about science and society, and it's called The Balloon String Theory. So if you could please give a warm welcome to Maya Elliot.
I've seen it many times before. You're having a perfectly laid-back, casual conversation, maybe about the weather or what's for lunch, when suddenly, out of the blue, someone drops complex science into your conversation and kills it. I say I've seen it many times before, because that used to be me. I used to drop science bombs all the time. It's kind of like photobombing, but instead of ruining someone's ruining someone's photo with epic timing, you're ruining someone's conversation with epic science. Not on purpose, of course. I was just trying to spice things up. So if someone complimented me on my top, I'd launch into the topic of nanotechnology and textile industry and the limitations of polymer nanofibers. Now, this all changed about 3 years ago, after I just finished my first year at university, when one of my science bombs blew up spectacularly in my face. And today I'd like to talk to you about how that experience changed my idea of what it means to be a scientist, and how I went from alienating myself with science to connecting with people through science. So it was a few years ago, and I'd gone to Holland, and my whole family had gathered for my sister's birthday party. There were balloons, and there was cake, and kids running around everywhere. And I remember that my gran was sitting next to me when she asked me the question, how university was going. Now, you may not see it, but I took this as a clear invitation to initiate launching sequence on my new favourite topic, epigenetics. I was mistaken. I was about 3 sentences in when my gran, who, bless her, is the most honest woman I know, just stopped me and said, "Dear, don't talk to me about that. I'm too old to understand such things." And turned around and started talking to my cousin about his balloon. Classic science bomb. Now, I was taken aback. How could you not be interested in DNA methylation patterns and histone modifications and chromatin dynamics? And how come my own relative was blatantly more interested in a balloon when the guy at the petrol station this morning seemed fascinated by my talk? At this point, my little cousin handed a balloon over to my gran, and it felt like I too had a balloon. But when I'd offered it to my gran, she'd rejected it. I didn't understand why. Surely science is a story of our very existence. How could she not share my passion? I realized at that moment that maybe if I wanted my nan to take that balloon, I'd have to pass it to her in a different way. And this was the seed for my own little string theory. So I'd like you to imagine that this balloon here represents science. Now, the string is how we communicate that science, how we pass it on to others. As scientists, we love collecting these balloons and we love showing them off. We spend our lives in pursuit of knowledge, inflating our balloon as we acquire more and more information. But the thing is that we're often so preoccupied with the balloon that we forget about the string. And surely, the string is as important as the balloon, because without the string, the balloon just floats away. Without communication, science is lost on everybody. So I decided, in order to share my balloon with my gran, I'd have to take a completely new approach. I went back to basics and decided to come up with a 3-step plan. This here is the epigenetics balloon that I wanted to share with my gran. Now, technical difficulty. Now, this balloon here was passed to me in a lecture. Now, the thing is in lectures is that we're passed the balloons and the means to inflate them, but not the string. You see, if you've studied science, then you already have your own strings at home which you can tie that information in that balloon onto. I'd attempted to pass my gran a balloon without a string. So the first step was to let a little bit of air out of the balloon. You see, not all the details are necessary to tell my story. Now the thing is that if you let too much air out of the balloon though, it'll deflate. And there's no point handing someone a string with a deflated balloon on the end. So you need to inflate it enough that the balloon will float. You need to take out enough information that it's simple, but not so much that it becomes simplistic. So the next step, once my balloon was an ideal size, was to create the string. I came up with all different kinds of metaphors, analogies, stories, but every time my string became too long or too tangled or not strong enough to tie all the information in the balloon together, until I found the perfect string. And then my final step, I added a hook. Now the hook allows the information in the balloon to be easily linked to something relevant in people's lives, or at least something that they're familiar with. But it also serves 2 purposes. First of all, it can be used to lure people in, to get people interested in your balloon. But secondly, it can also act as an anchor, because once someone can tie the balloon to themselves, or to something that's relevant in their lives, it'll stop the balloon from floating away. And that is when information becomes knowledge. Now, my gran and I, we'd never been especially close to each other. So I was absolutely adamant I was going to share that balloon the next time that I saw her. The next time I saw her was a couple of months later at her 50th wedding anniversary. Now, about halfway through the day, my gran introduced me to her childhood friend. And I asked her if she too, like my gran, was born during the Dutch hunger winter of 1944. She was, and they were both curious why I wanted to know. I said, "Did you know that the Dutch hunger winter might have changed your DNA?" I'd cast my hook. So, can I just get a show of hands who is familiar with the concept of epigenetics? Okay, well, for those of you who didn't bring your own strings today, allow me to provide one. I'd like you to imagine that every cell in your body is reading a newspaper called the Daily News. It's made up of articles called genes, and there are tens of thousands of these articles in the Daily News archives, or DNA. But the readers, your cells, only want to read the articles that they are individually interested in. And this is where epigenetics comes in. Epigenetics is the editor of that newspaper. The editor determines which of the articles get published and which don't, based on the type of cell and its interests. So, for example, an eye cell doesn't want to read articles on hair follicle production any more than my Dutch gran would want to read articles on British politics. So, the editor is extremely active during our lifetime, especially during our development. So, for instance, when we're in the womb, or during puberty, or during menopause. But the editor can also make editorial changes in response to a change in our environment or our lifestyle. So, for instance, regular exercise encourages the editor to publish articles on articles on fat burning, while smoking can actually suppress the publication of articles that fight cancer. But one of the most striking editorial changes can occur in response to a famine, like the Dutch hunger winter of 1944. So for those of you who aren't familiar with the Dutch hunger winter, towards the end of the Second World War, a Nazi blockade cut off food and fuel supplies to the west of the Netherlands, leading to adults having to survive on about 500 calories a day for months on end, and thousands of people died. Now, my gran wasn't born during the Dutch hunger winter, but she was conceived during the Dutch hunger winter. Talk about bad timing. But during the first 3 months of her development in the womb, her editor will have made editorial changes which improved her chances of survival in a world where food was scarce. So, for example, suppressing articles on energy metabolism while publishing articles on energy storage. And because of this, my gran and many others who were born around this time struggled with their weight later in life because all their energy was being stored and not metabolized. By the end of my story, my gran was in raptures. She had always struggled with her weight. And it wasn't her fault. It was her editor. And as it turned out, many of the people at this 50th wedding anniversary also struggled with their weight because of these editorial changes. Everyone else had somehow found a way to grasp onto my balloon and had linked it to themselves. And in doing so, they'd made a connection with each other through science. Not everyone was so keen to grasp onto the strings, though. I overheard a conversation during dinner between some of the old folks, and one guy was exclaiming, "How can epigenetics be real? Because if your DNA changes, how would forensics work?" And one of my proudest moments ever was when my gran replied, "It's not the genes in your DNA that change, dear. It's just which ones are switched on and off." I had made a connection with my gran. Instead of science alienating us, it had brought us closer together. I'd like to point out now that if half-inebriated 70-plussers can grasp a scientific concept like epigenetics at a party, teaching complex science to kids in schools should be a doddle. But why should we teach kids about quantum mechanics or the human genome or nanotechnology? Because that's the world that they are going to grow up into. But secondly, kids have an innate desire to grasp onto balloon strings, to learn. I think that if we allowed kids to play with the information that is at their fingertips with online boom of information, that they could discover oceans and oceans of balloons out there. However, until scientists create those strings which allow them to grasp onto it, there will always be a misunderstanding for science, and this leads to public fear. But I think that playing is one of the most powerful tools there is for learning. And if we can get kids to play with science balloons from a young age, we could eradicate public fear of science within a generation. Thank you.
Thank you very much.
Thank you, Maya. That was really, really amazing.
Thank you.
Now, before you all get to grill Maya with your questions, we have a TED video for you.
The video will be of a speaker called Yuri Allen. Enjoy.
In the middle of my PhD, I was hopelessly stuck. Every research direction that I tried led to a dead end. It seemed like my basic assumptions just stopped working. I felt like a pilot flying through the mist, and I lost all sense of direction. I stopped shaving. I couldn't get out of bed in the morning. I felt unworthy of stepping across the gates of the university because I wasn't like Einstein or Newton or any other scientist whose results I had learned about, because in science we just learned about the results, not the process. And so obviously I couldn't be a scientist. But I had enough support, and I made it through and discovered something new about nature. This is an amazing feeling of calmness, being the only person in the world who knows a new law of nature. And I started the second project in my PhD, and it happened again. I got stuck, and I made it through. And I started thinking, maybe there's a pattern here. I asked the other graduate students, and they said, yeah, that's exactly what happened to us, except nobody told us about it. We'd all studied science as if it's a series of logical steps between question and answer. But doing research is nothing like that. At the same time, I was also studying to be an improvisation theater actor. So physics by day, and by night, laughing, jumping, singing, playing my guitar. Improvisation theater, just like science, goes into the unknown. Because you have to make a scene on stage without a director, without a script, without having any idea what you'll portray or what the other characters will do. But unlike science, in improvisation theater, they tell you from day one what's going to happen to you when you get on stage. You're going to fail miserably. You're going to get stuck. And we would practice staying creative inside that stuck place. For example, we had an exercise where we all stood in a circle, and each person had to do the world's worst tap dance. And everybody else applauded and cheered you on, supporting you on stage. When I became a professor and had to guide my own students through their research projects, I realized again, I don't know what to do. I'd studied thousands of hours of physics, biology, chemistry, but not 1 hour, not one concept on how to mentor, how to guide someone to go together into the unknown, about motivation. So I turned to improvisation theater, and I told my students from day one what's going to happen when you start research. And this has to do with our mental schema of what research will be like. Because you see, whenever people do anything, for example, if I want to touch this blackboard, my brain first builds up a schema, a prediction of exactly what my muscles will do before I even start moving my hand. And if I get blocked, if my schema doesn't match reality, that causes extra stress called cognitive dissonance. That's why your schemas had better match reality. But if you believe the way science is taught, and if you believe textbooks, you're liable to have the following schema of research. If A is the question, and B is the answer, then research is a direct path. The problem is that if an experiment doesn't work, or a student gets depressed, it's perceived as something utterly wrong and causes tremendous stress. And that's why I teach my students a more realistic schema. Here's an example where things don't match your schema. You know, so I teach my students a different schema. If A is the question, B Stay creative in the cloud, and you start going, and experiments don't work. Experiments don't work. Experiments don't work. Experiments don't work. Until you reach a place linked with negative emotions, where it seems like your basic assumptions have stopped making sense, like somebody yanked the carpet beneath your feet. And I call this place the cloud. Now, you can be lost in the cloud for a day, a week, a month, a year, a whole career. But sometimes, if you're lucky enough and you have enough support, you can see in the materials at hand, or perhaps meditating on the shape of the cloud, a new answer. See, and you decide to go for it. Experiments don't work, experiments don't work, but you get there. And then you tell everyone about it by publishing a paper that reads A_C, which is a great way to communicate, but as long as you don't forget the path that brought you there. Now, this cloud is an inherent part of research, inherent part of our craft, because the cloud stands guard at the boundary. It stands guard at the boundary between the known and the unknown. Because in order to discover something truly new, at least one of your basic assumptions has to change. And that means that in science we do something quite heroic. Every day we try to bring ourselves to the boundary between the known and the unknown and face the cloud. Now notice that I put B in the land of the known, because we knew about it at the beginning. But C is always more interesting and more important than B. So B is essential in order to get going, but C is much more profound, and that's the amazing thing about research. Now, just knowing that word, the cloud, has been transformational in my research group. Because students come to me and say, Uri, I'm in the cloud. And I say, great, you must be feeling miserable. But I'm kind of happy, because we might be close to the boundary between the known and the unknown, and we stand a chance of discovering something truly new. Since the way our mind works is just knowing that the cloud, is normal, it's essential, and in fact beautiful, we can join the Cloud Appreciation Society, and that detoxifies the feeling that something is deeply wrong with me. And as a mentor, I know what to do, which is to step up my support for the student, because research in psychology shows that if you're feeling fear and despair, your mind narrows down to very safe and conservative ways of thinking. If you'd like to explore the risky paths you need to get out of the cloud, you need other emotions: solidarity, support, hope, that come with your connection from somebody else. So like in improvisation theater, in science, it's best to walk into the unknown together. So knowing about the cloud, also learn from improvisation theater a very effective way to have conversation inside the cloud. It's based on the central principle of improvisation theater. So here improvisation theater came to my help again. It's called saying yes and to the offers made by other actors. That means accepting the offers and building on them. Saying yes and. For example, if one actor says, here's a pool of water, and the other actor says, no, that's just a stage, the improvisation is over. It's dead. And everybody feels frustrated. Saying, that's called blocking. If you're not mindful of communications, scientific conversations can have a lot of blocking. Saying yes and sounds like this. Here's a pool of water. Yeah, let's jump in. Look, there's a whale. Let's grab it by its tail. It's pulling us to the moon. So saying yes and bypasses our inner critic. We all have an inner critic that kind of guards what we say, so people don't think that we're obscene or crazy or unoriginal. And science is full of fear of appearing unoriginal. Saying yes and bypasses the critic and unlocks hidden voices of creativity you didn't even know that you had, and they often carry the answer about the cloud. So you see, knowing about the cloud and about saying yes and made my lab very creative. The students started playing off of each other's ideas, and we made surprising discoveries in the interface between physics and biology. For example, we were stuck for a year trying to understand the intricate biochemical networks inside our cells. And we said, we are deeply in the cloud. And we had a playful conversation where my student Shai Chanel said, well, let's just draw this on a piece of paper, this network. Right? Instead of saying, but we've done that so many times and it doesn't work, I said, yes, and let's use a very big piece of paper. And then Ron Milo said, let's use a gigantic architect's blueprint kind of paper. And I know where to print it, and we printed out the network and looked at it, and that's where we made our most important discovery. That this complicated network is just made of a handful of simple repeating interaction patterns, like motifs in a stained glass window. We call them network motifs, and they're the elementary circuits that help us understand the logic of the way cells make decisions in all organisms, including our body. And soon enough, after this, I started being invited to give talks to thousands of scientists across the world, but the knowledge about the cloud and saying yes and just stayed within my own lab. Because you see, in science, we don't talk about the process, anything subjective or emotional. We talk about the results. So there's no way to talk about it in conferences. That was unthinkable. And I saw scientists in other groups get stuck without even having a word to describe what they're seeing. And their ways of thinking narrowed down to very safe paths. Their science didn't reach its full potential, and they were miserable. I thought, that's the way it is. I try to make my lab as creative as possible, and if everybody else does the same, science will eventually become more and more better and better. That way of thinking got turned on its head when by chance I went to hear Evelyn Fox Keller give a talk about her experiences as a woman in science. And she asked, why is it that we don't talk about the subjective and emotional aspects of doing science? It's not by chance. It's a matter of values. You see, science seeks knowledge that's objective and rational. That's the beautiful thing about science. But we also have a cultural myth that the doing of science, what we do every day to get that knowledge, is also only objective and rational. It's like Mr. Spock. But when you label something as objective and rational, automatically the other side, the subjective and emotional, become labeled as non-science, or anti-science, or threatening to science, and we just don't talk about it. When I heard that science has a culture, everything clicked into place for me, because if science has a culture, culture can be changed. And I can be a change agent working to change the culture of science wherever I could. And so the very next lecture I gave in a conference, I talked about my science, and then I talked about the importance of the subjective and emotional aspects of doing science and how we should talk about them. And I looked at the audience, and they were cold. They couldn't hear what I was saying in the context of a 10 back-to-back PowerPoint presentation conference. And I tried again and again, conference after conference, but I wasn't getting through. I was in the cloud. And eventually I managed to get out of the cloud using improvisation and music. Actually, since then, every conference I go to, I give a science talk and a second special talk called Love and Fear in the Lab. And I started off by doing a song about scientists' greatest fear, which is that we work hard, we discover something new, and somebody else publishes it before we do. We call it being scooped. And being scooped feels horrible. It makes us afraid to talk to each other, which is no fun because we came to science to share our ideas and to learn from each other. And so I do a blues song, which called Scooped Again. And I ask the audience to be my backup singers, and I tell them, your text is scoop, scoop. Sounds like this, scoop, scoop. Sounds like this, I haven't scooped again, scoop, scoop. And then we go for it. I haven't scooped again, scoop, scoop. I've been scooped again. I've been scooped again. I've been scooped again. Oh, mama, can't you feel my pain? Heavens help me, I've been scooped again. Thank you. Thank you for your backup singing. So everybody starts laughing, starts breathing, notices that there's other scientists around them with shared issues, and we start talking about the emotional and subjective things that go on in research. It feels like a huge taboo has been lifted. Finally, we can talk about this in a scientific conference. And scientists have gone on to form peer groups where they meet regularly and create a space to talk about the emotional and subjective things that happen as they're mentoring, as they're going into the unknown, and even started courses about the process of doing science, about going into the unknown together, and many other things. So my vision is that just like every scientist knows the word atom, that matter is made out of atoms, every scientist would know words like the cloud, saying yes and science will become much more creative, make many, many more unexpected discoveries for the benefit of us all, and will also be much more playful. And what I might ask you to remember from this talk is that next time you face a problem you can't solve in work or in life, there's a word for what you're going to see, the cloud. And you can go through the cloud, not alone, but together with someone who's your source of support to say yes and to your ideas, to help you say yes and to your own ideas. To increase the chance, well, through the wisps of the cloud, you'll find that moment of calmness where you get your first glimpse of your unexpected discovery, your sea. Thank you.
Please now welcome back Maya on stage for the Q&A session. If any of you have a question or want to make a comment or add something to what has been said, please just raise your hand and one of our volunteers will get the microphone to you.
Or you can always tweet us at #TEDx Surrey University.
So anyone. Okay.
Yes?
So how did you become so passionate with science in the first place? I mean, what started all this?
I think I've always had an interest in science since I was very young. And I think part of it's just, it's also a personality thing, I guess. If you're very interested, I didn't have a very broad range of interests when I was a kid. So I just kind of immersed myself in science, and I understood science because science is very logical, and I'm a very logical person. I didn't get a lot of, I didn't connect easily with other people because I have Asperger's. So I tended to find that through science, I understood all of that. I didn't understand like normal social interactions as well. But I think that by talking about science and by sharing my science, that was something that really allowed me to connect with other people and improve in social interactions as well. So I think that's the reason why I'm so passionate about it now.
Thank you so much for your question. Any other questions?
Comments are welcome as well.
You mentioned talking to kids about the importance of science. So how would you describe epigenetics to kids?
Now, with epigenetics, I think when you're explaining any kind of science to kids, I think it's very important to make it playful and to make it creative. So one way that I would approach teaching epigenetics to kids is I would stick with a metaphor that they're familiar with, so maybe the newspaper, but I would maybe make them construct their own newspaper, put together the articles themselves, provide articles, and then they can, based on maybe a character description, put together a newspaper, or maybe I provide them with a funny newspaper with funny articles about the different genes, and then they could, from that, analytically derive what that person's lifestyle was like, perhaps. And that's, I think by doing it through playing, that's one of the best ways to get kids to learn about these things.
Thank you so much for your question. Anyone else? Any questions?
In the video, Uri talked about the problem of scientists not talking to each other. Have you encountered that? Because I know you're at university, so is it present even at the university level?
I think when I'm talking to my peers about science, one of the things which is already prevalent and which becomes a lot worse as we get further and further in our career is the fact that we kind of like to discuss things, but we like to put each other's ideas down as well before they really get a chance to get a hold. So if I'm talking about this new kind of or the prospects of epigenetics or the implications of nanotechnology or something, someone else would be very quick to say, oh no, that wouldn't work because, oh no, there's no scientific evidence for that, or oh no, it's only in mouse models, it hasn't been proven in human models yet. But I think that one of the things that we need to do is nurture, like you said, say yes and, instead of just putting each other's ideas down. And I think that hopefully with more of these kind of talks going around, this will improve at a university level as well.
Thank you. Yes, we have a question.
So how do we know if the balloons we grab onto or the balloons kids grab onto are truthful?
Sorry?
Are truthful? How do we know we can trust the balloons?
So that the information is right. I think with the age of information, at the moment we've got the internet, we've got so much information, and I think that one of the risks is that there are people out there who do fabricate information or distort information and fill up a bunch of balloons with just rubbish and then pass it off to be real. So I'm talking about people who deny climate change, people who take information out of context and then work a really lovely string that people want to grasp onto. But that balloon is just full of rubbish. It won't float. So I think that in order to prevent this kind of thing from happening, I think that scientists need to step up and provide the strings so that other people, frauds and quacks, don't have that window of opportunity. But I think also that what we're doing at the moment, exposing this bad information, I just don't think that that's enough, because until we provide new strings as scientists, people won't want to let go of what they know, what they've already grasped onto.
Thank you so much for your question.
Anyone else? You can also tweet your questions if you just put a hashtag TEDx Surrey University. If you don't want to speak up and talk into the microphone, you can just tweet us.
I know how nerve-wracking that is. I think I'm
Or
shaking.
you can find me in the lunch break. That's
Yes.
That's an alternative.
We have another question.
Can I ask a science question? You described the experience that your grandmother had of growing up in the Dutch hunger winter, which changed her genetics.
Mm-hmm.
But once the hunger winter had passed, why didn't her genetics then change back again and stop the problems with the weight that she had in later life?
Well, the thing with epigenetic changes is that they're quite hard to, especially when they occur during the first or second trimester of pregnancy, they're quite hard to undo, because it basically changes the conformation of the DNA and it kind of sets it. Now, it can be, there are certain things like exercise or certain diets which can actually change the epigenetics of your DNA. However, this is a very slow process, and our DNA, our epigenetic editor, over the course of human history has had to deal with sudden famines, either due to exceptionally harsh winters or main prey going extinct, or these kind of things. And it's had to make that switch very quickly from lots of food to no food. However, in these cases, the switch from no food back to a time of plenty was very gradual. Whereas with the Dutch hunger winter, that switch back was very sudden. All of a sudden, when the Nazi blockade was lifted, there was food again. So our DNA didn't have time to make that change back. And I think that if my grandmother had been aware from a young age that this is what had happened to her DNA, and she had invested time in maybe exercising more or eating certain types of food and avoiding others, then she would have maybe slowly been able to undo these epigenetic changes. But we're still learning a lot about it, so it's we're still, and because human epigenetics is of course difficult to study because it's only been around for about a decade, I think that we need to have another generation worth of data before we can make any firm claims.
We have another question over here.
What currently emerging science do you think needs to be communicated to younger people at the moment?
Yeah, so what kind of upcoming science? Sorry? That's a really good question. I personally see incredible potential in communicating just the quantum theory to kids, because we use it in computers. It's seeing a massive boom in our everyday civilization. And if kids can't understand it, then very few people, it will just remain the very, very few people who can understand it at the moment. So I think that there's a lot of science communication going on there. But I personally think from a health perspective that we should be teaching kids much more cell biology, much more about genetics, because these are things that they can grasp hold of and which I think will make a difference for an entire generation. We are living so much longer nowadays. Our bodies aren't naturally equipped to live this long, and we're going to have to start taking care of ourselves on a cellular and on a genetic level if we're going to stay healthy and live to 100.
Thank you. There was a question at the back, if I'm not mistaken.
You mentioned just now about your grandmother and her change in DNA due to the hunger thing, the famine.
The hunger winter, yeah.
Yeah. So did that affect your mom's DNA as well?
That's a really good question, and like I said, this is why we're so excited to be learning more about it with the next generations, because the transgenerational effects aren't very well understood. We think that about 1% of all epigenetic changes are inherited by the next generation. However, it tends to be the epigenetic changes which are involved in survival. So the epigenetic changes due to the hunger winter were ones that tended to be passed on because that was a survival change. So I think that we're still waiting on the data. My mum didn't struggle with her weight, but I know that my aunties did. And but we'd have to look at their DNA as well and then find out more from that. I think by the time that we hit, my sisters and myself were okay, I think. But no, I think that these changes can be inherited, but I think it's to a much lesser degree. Generally, when fertilization occurs, all the epigenetic changes are stripped off and kind of like rebooted. But yeah, 1% remains, and that can have a really big impact.
Thank you so much for your question.
We have a Twitter question, if it comes up.
I think it was related
In the meantime, have you collected samples from your family and tested them to see the epigenetic influences?
At what age did you get interested in science and something else?
Oh, okay. I pick which one you want. Right. So which question shall I answer? At which age? Like I said, I became interested in science from quite a young age because it was something that I understood. But I think the first time that I looked down a microscope, when I was about 12, I think that was for me when everything changed, and I realized that there was a whole new world out there. And I've gone even deeper from the cellular level to genetics level now, and it's just never ending. It's huge, it's expanding, and I think that anyone who is interested in science, everyone who's here today obviously will have that kind of, that passion for knowing more. But I think that every child has this interest in science from a very young age, and that we should nurture that a lot more. Not make science scary, but make it fun.
Okay, there was a question, how do you become a science bomber?
Yes.
I think someone's interested in becoming one.
Just a tip, don't become a science bomber. You'll make yourself very unpopular. Yeah, basically, if you really want to annoy someone, anything they say, just find some link to your area of science. There is always a link, I promise you. And if you just, yeah, that's probably the best way if you don't want people to talk to you anymore. Just science bomb them whenever you can. Well, oh yeah, watch lots of QI. Just accumulate random facts that... Actually, QI is quite interesting.
See what you did there. The other question was, do you think science is a male-dominated field?
This is, I think, when we're talking about scientists, I know that many scientists, when it comes to scientists, it tends to be kind of 50-50 males and females up to a certain point. So at university level, at bachelor level, 50-50. And then what we see is that a lot of women drop out of science because they prioritize having a family, or they're married to scientists and one of them has to stay at home, and it's usually the man who keeps going to work. So the higher up in the hierarchy you go, the fewer and fewer women there are. Now, I'm hoping that this is going to change because I think that nowadays it's becoming more and more equal. And I think that it's more common for men to also take on the task of rearing children as well. So I don't think that that women who are at the top necessarily will have to give up family life in the future. I'm hoping this anyway.
Yes, question at the front here.
Going back to epigenetics, do you think in the future, once people know more about it, they'll be able to kind of exploit the benefits from it?
Yeah, I definitely think so.
That's the short answer.
So what we're doing at the moment, see, some cancers are caused, like I said, by epigenetic changes. So smoking can suppress a publication or suppress certain genes which basically prevent cancer. So check yourself for mutations and that kind of thing. And this is how mutations occur and then cancers form. Now, what we're doing is we're just basically we know the tools that the editor, that epigenetics uses. They're called histone modifications and methylation tags. What we're basically doing in these cancers is kind of like a last term resort, is just chucking a bunch of those methylation tags at someone's cancerous cells in the hope that it will turn off genes that had previously been switched on, or the other way around. Now, at the moment, we can't target it, but I think that when we can target that, then we can give our muscles a workout without even actually exercising, because we can just convince those cells that they've had the benefits of exercising when they haven't. I think that we could use it to increase energy. I think we could use it to improve fertility. So I definitely think that in the future, epigenetic therapy will be a very big thing. The problem right now is targeting it, but these things, when there's money to be made in it, these things can go quite quickly.
Any other questions?
Then I guess thank you all for your
Thank you very much. Oh, one more.
One more question.
One more. That'll be the last question.
Do you feel like there's almost like a social pressure for science to be uncool in an early age? Because I found in primary school and secondary school especially that science was seen as sort of like as uncool, and maths was uncool, and it wasn't cool to be clever. I feel like it kind of changed with university, but do you feel like there's a way we can get around that? Or do you even feel that it's not really a thing? It was just my experience.
No. I definitely agree. And I think that one of the reasons why this is because if people don't get it, they don't want it to be cool. They think it's very cool if other people do get it because it makes them feel bad that they don't get it. And I think also it can be taught in a very dull way. I mean, I know when I was in secondary school, I had a teacher who was incredibly dull. And I could see why people didn't think that science was cool, because she didn't make it cool. Like, she'd be telling us about, you know, reproductive biology, and we'd all be falling asleep when you can make that so much fun. I mean, but also just things like plant biology, and it was told in like a monotonous voice. That isn't cool. What you need is you need people to make it cool. And I think that also by getting kids to play with it and actually mastering it, you know that feeling when you get something? That kind of, you know, that aha moment? I think that that's something which can really motivate people to get interested in science, to talk about it, and to share it. And I think that that's how we're going to make science cool.
Thank you very much, Maya. Please give it up. And now we've come to our first break. This one is the 15-minute break, and we'd like to invite you to the foyer outside the theatre, where there will be some refreshments. We would ask you not to bring back in any drinks or foods. It's against uni regulations. So see you back here in 15 minutes.
Probably around 20? Yeah, 12:20.
12:20.
Thank you. So, welcome back, everyone. Yep. So, hope you all had a good break and all refreshed and ready for our second speaker.
Our second speaker is University of Surrey's very own Professor of Physics, Ben Murden, and his talk is called
Cats Wanted, Dead and Alive, Quantum Technologies for the Undecided. So
Please give a warm welcome.
Thanks very much. Yes, I want to talk to you about quantum physics, and we've heard a few people mention quantum physics already as something that we ought to be more aware of, I suppose, and understand a bit better. And maybe I should just ask you, first of all, could you raise your hands if you think you understand quantum physics? Okay, well, one or two, that's great. Okay, it was sort of a trap, really, if I asked you that question, because somebody much smarter than I did once said, if you think you understand quantum physics, then you actually haven't understood it properly. But I want to talk to you today about some quantum physics effects, and the reason why I find it so fascinating is because of the fact that it's mind-boggling. We aren't really used in our everyday lives to encounter this, these kind of properties, but at a small scale, small things like atoms and electrons can be in two places at once and do two different things at once. And I don't know what your superpower would be, but this is my friend Ruth. She's a singer and musician, and she would really love to be able to have her own band where she plays everything at once. And I just would like to sort of offer to you the concept that you could be really, really powerful and you could do really amazing things if you could obey the laws of quantum physics yourself. And we're trying to move towards that situation where we have bigger and bigger things obey the principles of quantum physics. Go over the next slide, please. Okay, so quantum physics is all around us, actually, and you will have encountered quantum physics several times. You'll have seen it yourself whenever you walk around under sodium street lamps. The thing that determines the color of those sodium street lamps is quantum physics. And here is another example. This might seem like the physics of something really big, but actually the red stuff in this picture is hydrogen. It's being stimulated by the hot blue things in the picture, the stars, and the color that they emit is a bright red color. Astronomers call it the H-alpha line. It's 656 nanometers if you're scientifically minded. So, some people often ask me, what's your favorite color? And I reply 488 nanometers, but I don't know what your response would be. The reason why the hydrogen atoms do this is because of the laws of quantum physics. Can I have the next slide, please? So here we show some waves. The reason why the hydrogen atom does that is because it's behaving like a wave. And you're used to wave physics, so you understand the way that musical instruments work, I bet. If you pluck a guitar string in the middle of the string, it will do a motion, the fundamental mode of the string, and you can pluck it maybe a quarter of the way along and 3/4 of the way along and let go, and it will play the first harmonic. That's 1 octave higher. And all that the electron that's orbiting around the hydrogen atom does is just a 3-dimensional version of exactly the same thing. So there are specific oscillations that the hydrogen atom can perform. And when the atom jumps from one state to another, it emits light of a very specific color, corresponding to the energy jump between those two states, and that's what gives you the very characteristic lines. And different atoms emit different lines. That's why sodium emits this yellow light that you see in streetlights, and why hydrogen emits the red that you saw on the previous picture. Okay, so a great thing about waves, or the thing that makes them different from our sort of everyday experience of objects and particles, is that they produce interference. So if you add two waves together, they can cancel each other out, or they can amplify each other. So here's a picture where I've shown a pair of light sources, and they are producing an interference pattern. And you can sort of understand that in terms of waves. But if I said, now what if particles and objects could do the same sort of thing? Supposing I took a pair of footballers and I put them at one end of the football pitch, and I told them to shoot towards a goal. It would be really surprising if I could set up the goal in some place at the far end of the field where it would be impossible for the footballers to get the balls in. But actually atoms do exactly this. We could make a pair of sources of atoms, and we can fire the atoms out into space, and we can put a detector in the back of the space where we're firing the atoms, and we can set it up so that the atoms have no probability of going into the detector. Move the detector a little bit to one side, and then the atoms go through. So atoms on small-scale things obey this wave-like property. We're just not used to seeing that on a large scale. Can I have the next click? Now, you can also interfere waves in time as well. If you add two waves together, you can get new kinds of motion. So if you add the fundamental mode of your guitar string and the 1 octave higher, you can get a slightly jelly-like wobbling motion. And the same thing with the atoms. You can put them into a situation where they are doing two things at once. They are both in the low frequency mode and they are in the high frequency mode at the same time. So when a quantum physicist tells you that something can do two things at once and it can be in two places at once, I mean, what if I ask you that this first harmonic wave, where is the wave? You would say, well, it's sort of in two places. It's at the top of the string and it's at the bottom of the string. It's in both places at once. So when, as I say, a quantum physicist tells you things can be in two places at once or it can do two things at once, what they really mean is it's obeying wave physics. So here's a little guitar demonstration. You can see that if you click the button, the movie should start. Yes, so you pluck the guitar string in the middle and you see it just does the fundamental mode of vibration if I play it in slow motion. We can see that putting your finger on the 12th fret, that's the one with the two spots, that's exactly halfway along, plays this fundamental mode. But I can play the second harmonic, the first excited, say, 1 octave higher by plucking the string a quarter of the way along. Now I can do something a bit more complicated. I can play a harmonic chord, both notes at once. If I pluck the string a quarter of the way along, but I lightly touch in the middle. Now you can see that the wave motion is flowing back and forth along the string. It's actually playing both notes at once. If I had recorded the sound of the guitar at the same time as making this movie, you would actually be able to hear the difference. In the first case, you would hear a low note. The second case, you would hear a high note. And then with the harmonic chord, you would hear both notes at the same time. Now, okay, these wave-like properties, what can they do for us? So one of the fathers of quantum physics, Erwin Schrödinger, thought of an experiment that you might be able to get us this small-scale properties to the larger scale. And he imagined a situation, what would happen if I took an atom, and the atom, I put it into this situation where it's doing both things at once. It's both in the relaxed state and it's in the excited state at the same time. And supposing I take a detector, which is capable of sensing which of the two states the atom is in, then presumably the detector will be triggered and untriggered at the same time. And supposing I connect it via some mechanism to a bottle of poison, and the bottle of poison can be then both broken and unbroken at the same time. And what if I put a cat next to the bottle of poison? The cat can then be both poisoned and not poisoned. And strange things about quantum physics are that if you don't look at the situation, if you don't make a measurement, then the objects can be in these two states at once. So the cat ought to be both alive and dead. If I put all this stuff into a box, close the box, if I put the atom into the excited state, gradually the atom will relax as a function of time. The probability of being in the excited state will decay, but the atom is actually in both states at once, and therefore the cat should be both alive and dead at once. Actually, Schrödinger postulated this thought experiment in order to try to show how absurd quantum physics was. He actually didn't believe it. He thought there was a fundamental problem with quantum physics. Actually, we now believe that it's true. You can put large-scale things in two states at once. Now, why has nobody ever done this experiment? Well, okay, apart from it being inhumane, it's actually a really, really, really hard experiment because of the number of atoms that are inside a cat. I talked about the ability of very small objects to obey wave-like properties. There are 10 to the power of 26 atoms inside a cat. That's a 1 with 26 zeros on it. That's a lot of things to put into this very carefully controlled state. And the other reason why nobody's done it is because it's actually a really boring experiment. The idea that you would set up the atom in the excited state, put everything into the box, close the box, wait for the thing to be in two states at once, and then eventually open the box and see what state the cat is in. Once you open it and look inside, the cat will then decide either to be alive or dead. And sometimes you'll measure alive, and sometimes if you repeat the experiment, you'll measure dead. And the sum of those two probabilities will be 100%. So what? Who cares? But maybe we can add control. Supposing we can control whether or not the cat is alive, or how much alive it is. Now we start to get to something really interesting. And in fact, this kind of idea has actually been around for a long time. I don't know if anybody here has ever had an MRI scan. If you've had an MRI scan, you will have been put into a machine that actually puts all of the hydrogen atoms in your body into the state where they're both spinning clockwise and anti-clockwise at the same time. And when they do that, when they're in this superposition state, they emit radio waves you can detect, and therefore you can see how much hydrogen there is and where it is. And that's what gives you the contrast on the MRI image. It's telling you where the water is in your body. And where there's water, you see radio waves, and when there isn't any water, you don't see them. And where the radio waves have come from is just the hydrogen atoms that are in this superposition state. So it gives us some really interesting technologies. But there isn't any information technology that uses this idea yet. Information technology we're pretty familiar with. It makes our silicon computer chips. And here's some pictures of, actually not quite the current smallest, but this is from a couple of years ago, one of the smallest transistors that had ever been made, 50 nanometers. Now we're down to about 17 nanometers being the smallest transistors. That's 20 billionths of a meter. It's extremely small. And the information inside those transistors is carried by whether or not the transistor is on or off. It gives us the ones and zeros of binary information. And we're getting to the point now where we can think of making transistors where the information, instead of being 0 or 1, the transistor being on or off, we have transistors where the transistor is both on and off at the same time. Next slide, please. And even better than that, we can actually couple transistors together to get pairs of transistors. Imagine if I have a pair of atoms. There's now 4 pieces of information can be stored in just 2 atoms, because I need to keep track of the probability that both atoms are excited, that the left one is excited and the right one is relaxed, left relaxed and right excited, or both relaxed. That's 4 different probabilities I need to keep track of. That's 4 pieces of information are in that system. Whereas if I have 2 ordinary transistors, there's only 2 pieces of information. It's, the left one is on or off, and the right one is on or off. And you can imagine if I have 3 transistors, then there'd be 8 pieces of information, and so on. It goes up exponentially. So quantum transistors and quantum computer registers would be really powerful for quantum information technology. And we're getting to the point where we can engineer single atoms inside silicon chips. Here's my friend Philip. He's a research student at University College London, and we've overcome the challenge of being able to position an individual atom on the surface of a silicon chip now. Here you see a micrograph that shows a silicon crystal. The surface of the silicon crystal is illustrated. You see each individual silicon atom in the crystal. And Philip has positioned on the surface a single atom, a single impurity atom, and it's bulging out at the center. It's also causing the neighboring silicon atoms to bulge out a little bit as well. But there's just one single impurity there that is positioned with atomic precision. And that's a really amazing engineering challenge. It's a bit like, it's actually exactly the same scale factors as trying to manipulate individual ping pong balls on the surface of the sun from Earth. So it's a really amazing feat of engineering. And how do you pluck these atoms? How do you cause them to go into this 2 states at once, and this strange-like oscillation of being both excited and relaxed? Well, you need some clever lasers. You use laser pulses to do the plucking of the string. And here are some results. I hope I don't get scooped. We heard the previous speaker on the TED conference was talking about being scooped. These are unpublished results, so please don't tell anybody. But we've demonstrated now with these individual atoms that we can get these interferences. So that the data here shows clear oscillations. And I've shown here the spectrum of the oscillations, showing that we get this very clear note lasting for long times after the original plucking of the string. And this is evidence that we have quantum interference in these individual atoms. So we're getting very close now to the point where we can make a big computer register. And I'd just like to end with a little bit of a movie to illustrate how you might use or imagine the power of a quantum computer.
Always so many things to do. Imagine Imagine how efficient you'd be if you could split into multiple versions of yourself, the ultimate in multitasking. And what if you could then get your friends to do the work for you by getting them to split so that they could be in two places at once? This magical behavior is exactly what goes on in the quantum world. Atoms can indeed be made to split into several versions of themselves. We say they're in a superposition of different states. They can also spread themselves over multiple locations and entangle with other atoms. This is the basis of a quantum computer, in which all possible computations can be carried out at once.
Okay, so that was maybe a bit futuristic. It's going to be a long, long time before we can clone individual people, because, as I say, the difference between a big human person and a small atom is quite large. But actually, we only need to get of the order of 100 atoms into this two states at once in order to be able to make the most powerful computer that you could possibly imagine. Inside your ordinary mobile phone, there are billions of transistors, but I only need 100 quantum transistors in order to be able to beat that phone. And so we're getting to the place where we can really imagine a revolutionary change in our quantum technologies. But so I started this talk by talking about the mental challenge, and actually that's what really motivates me in doing this research. Is I find it just so strange, the quantum ideas of being in two places at once and doing two different things at once, and trying to understand what's going on when I do my experiments is sort of a surreal, idea, and so academic research in this area I find a fascinating thing, and so that's why I love to work in this area. And I should also say that something that the previous speaker mentioned, we should be trying to teach smaller children these kind of ideas. I think I've actually had an experience of this going to science fairs like the Big Bang Science Fair and the Royal Society Summer Science Fair, and meeting children and telling them these ideas about being in two places at once. They don't bat an eyelid. So the more we expose them to this kind of thing at an early age, the better we'll all understand quantum physics. So I'd just like to thank my sponsor. Can you get to the next slide? Yes. So my sponsor, EPSRC, and my friends who generated these results. And thanks very much for your attention.
Thank you very much. And now, before the Q&A, to the second video. This one is by Erin O'Connell, and it's called "Making Sense of a Visible Quantum Object."
This is a representation of your brain, and your brain can be broken into two parts. There's the left half, which is the logical side, and then the right half, which is the intuitive. And so if we had a scale to measure the aptitude of each hemisphere, then we can plot our brain. And for example, this would be somebody who's completely logical. This would be someone who's entirely intuitive. So where would you put your brain on this scale? Some of us may have opted for one of these extremes, but I think for most people in the audience, your brain is something like this, with a high aptitude in both hemispheres at the same time. I mean, it's not like they're mutually exclusive or anything. You can be logical and intuitive. And so I consider myself one of these people, along with most of the other experimental quantum physicists. We need a good deal of logic to string together these complex ideas, but at the same time, we need a good deal of intuition to actually make the experiments work. How do we develop this intuition? Well, we like to play with stuff, so we go out and play with it, and then we see how it acts, and then we develop our intuition from there. And really you do the same thing. So some intuition that you may have developed over the years is that one thing is only in one place at a time. I mean, it can sound weird to think about one thing being in two different places at the same time, but you weren't born with this notion, you developed it. I remember watching a kid playing on a car stop. He was just a toddler and he wasn't very good at it, and he kept falling over. But I bet playing with this car stop taught him a really valuable lesson, and that's that large things don't let you get right past them, and that they stay in one place. And so this is a great conceptual model to have of the world, unless you're a particle physicist. It'd be a terrible model for a particle physicist because, well, they don't play with car stops. They play with these little weird particles. And when they play with their particles, they find they do all sorts of really weird things, like they can fly right through walls, or they can be in two different places at the same time. And so they wrote down all these observations, and they called it the theory of quantum mechanics. And so, that's where physics was at a few years ago. You needed quantum mechanics to describe little tiny particles, but you didn't need it to describe the large everyday objects around us. This didn't really sit well with my intuition, and maybe it's just because I don't play with particles very often. Well, I mean, I play with them sometimes, but not very often. And I've never seen them. I mean, nobody's ever seen a particle. But it didn't sit well with my logical side either, because if everything is made up of little particles, and all the little particles follow quantum mechanics, then shouldn't everything just follow quantum mechanics? Yeah, I don't see any reason why it shouldn't. And so I'd feel a lot better about the whole thing if we could somehow show that an everyday object also follows quantum mechanics. So a few years ago, I set off to do just that. So I made one. This is the first object that you can see that has been in a mechanical quantum superposition. So what we're looking at here is a tiny computer chip, and you can sort of see this green dot right in the middle, and that's this piece of metal I'm going to be talking about in a minute. This is a photograph of the object, and here I'm going to zoom in a little bit. We're looking right there in the center, and then here's a really big close-up of the little piece of metal. So what we're looking at is a little chunk of metal, and it's shaped like a diving board and sticking out over a ledge. And so I made this thing in nearly the same way as you make a computer chip. I went to a clean room with a fresh silicon wafer, and then I just cranked away at all the big machines for about 100 hours. For the last step, I had to build my own machine to make this swimming pool-shaped hole underneath the device. This device has the ability to be in a quantum superposition, but it needs a little help to do it. Here, let me give you an analogy. You know how comfortable it is to be in a crowded elevator? I mean, when I'm in an elevator all alone, I do all sorts of weird things, but then other people get on board, and I stop doing those things because I don't want to bother them or frankly scare them. So quantum mechanics says that inanimate objects feel the same way. The fellow passengers for inanimate objects are not just people, but it's also the light shining on it, and the wind blowing past it, and the heat of the room. And so we knew if we wanted to see this piece of metal behave quantum mechanically, we're going to have to kick out all the other passengers. And so that's what we did. We turned off the lights, and then we put it in vacuum and sucked out all the air, and then we cooled it down to just a fraction of a degree above absolute zero. Now all alone in the elevator, the little chunk of metal was free to act however it wanted. And so we measured its motion, and we found it was moving in really weird ways. Instead of just sitting perfectly still, it was vibrating. And the way it was vibrating was breathing, something like this, like expanding and contracting bellows. I mean, by giving it a gentle nudge, we were able to make it both vibrate and not vibrate at the same time. Something that's only allowed with quantum mechanics. So what I'm telling you here is something truly fantastic. I mean, what does it mean for one thing to be both vibrating and not vibrating at the same time? So let's think about the atoms. So in one case, all the trillions of atoms that make up that chunk of metal are just sitting still. And at the same time, those same atoms are moving up and down. Now it's only at precise times when they align. The rest of the time, they're delocalized. So that means that every atom is in two different places at the same time, which in turn means the entire chunk of metal is in two different places. I think this is really cool. I mean, really. It was worth locking myself in a clean room to do this for all those years. Because check this out. The difference in scale between a single atom and that chunk of metal is about the same as the difference between that chunk of metal and you. So if a single atom can be in two different places at the same time, that chunk of metal can be in two different places, then why not you? I mean, this is just my logical side talking. So imagine if you're in multiple places at the same time. What would that be like? is how would your consciousness handle your body being delocalized in space? There's one more part to the story, is when we warmed it up and we turned on the lights and looked inside the box, we saw that the piece of metal was still there in one piece. And so, I had to develop this new intuition that it seems like all the objects in the elevator are really just quantum objects, just crammed into a tiny space. You hear a lot of talk about how quantum mechanics says that everything is all interconnected. Well, that's not quite right. It's more than that. And it's deeper. It's that those connections, your connections to all the things around you, literally define who you are. And that's the profound weirdness of quantum mechanics. Thank you.
So let's get started with the Q&A session. Ben, please come back on stage.
Okay, again, if anyone has any questions or comments, please raise your hand and we'll get the mic to you.
Mic. Where's the mic? All right.
Okay, it's on. It has been recently proposed that artificial intelligence will soon become so powerful that it will become capable of evolving independently of human input. So is your work on quantum computers contributing to the end of the human race?
Yes, so I've heard even funnier apocalyptic stories. As soon as the government learns how to put people into two places at once, then they'll be able to transport you out over the ocean and drop you in the sea. Because teleportation is somehow interconnected with quantum information. So there's all kinds of bad things that somebody might do once they get hold of quantum information. Actually, even closer to home, or even more closer to reality, is as soon as someone gets hold of a quantum computer, then they'll be able to crack all of your secure communications, because the RSA encryption that you use to talk to your bank will be able to be cracked, because you'll be able to factorize very, very large prime numbers. So we'll get to those kind of things long before we get to the artificial intelligence. I guess artificial intelligence is something that a quantum computer will be able to do, because one of the reasons why the ideas of quantum information started was because a very smart physicist, Richard Feynman, noticed that the complication of quantum objects gets more and more quickly, gets complicated much more quickly than our current computers are growing. So if you want to model a pair of atoms, you need 4 pieces of information. I described that in my talk earlier. And if you want to model 3 atoms, you need 8 pieces of information. And so if you want to model the motion of a single molecule of DNA, then that would be vast amounts of information, way more information than you could put onto all of the computers in the world at the moment. And so when we're modeling drug design, let's say, we can't do it at the fundamental level. We have to make lots and lots of approximations. And Feynman said, maybe one day we'll be able to make a computer that's based on quantum physics principles that will then be able to do that modeling for us. And of course, if we've got a computer that's based on those quantum physics principles, then it can actually act like the biological molecules. And maybe it can then learn. And so then maybe it can evolve in the way you said. But I think we're quite a long way away from that, and lots of exciting and useful and positive things will come out of it before the negative things.
Thank you for your question. Over to the... Oh, we have lots of questions for this round.
Also, don't forget to tweet us.
Yes.
Or hashtag TEDx Surrey University.
Are there any are there any dangers of being put in a quantum state that you could think of hypothetically? Even if it's just on a maybe molecular level, would it change a structure or?
Well, I suppose that any danger you can think of, if I'm now in 2 places at once, then I'll be able to experience twice the danger. Maybe that's the simple answer.
But would you be physically in 2 places at once? Would you? Because when we think of atoms, we think I think of it as matter, but would that matter not be halved?
No, so the way I think about this is that there is a probability wave, and the wave is the matter. There's no difference to me between the wave and the matter, because I can't do any measurements that will tell me that there's any difference. And the wave is extending physically over all of the space that you put it in. So if you've expanded the space and the wave is now extending over a bigger space, and it has a spread that is bigger than it was before, it will be able to experience everything all around it in the new space.
Okay.
In fact, I didn't go into how I want to make my quantum registers, but I want to be able to take one atom that's maybe in its ground state. Its neighbors will also be in their ground state. The way that I can get them connected is by expanding the wave. And so then they touch each other, and then they entangle, and they gain information about each other. So it's necessary that interactions increase in order for us to get this new kind of quantum technology.
Okay.
And I can imagine that molecules and atoms in a biological system would also experience whatever damage.
But they would revert back to their original state when they're taken out of the quantum state.
Well, not necessarily, no. What I want in my quantum computer is that they're in a different state from when they started. I want to sort of initialize the system with all of my quantum bits in their ground states. I then want to run the computer program, which has got laser pulses to pluck the string, as I was describing. Eventually, all of the registers, all of the atoms will end up in some complicated state. I then have to look at the atoms and see what the new state is. They're not all back in the original ground state. It would be a very boring computer program. So I want the thing to change, yes. I want evolution.
Great.
We have two questions at the back there. Yes?
Wait for the mic, please.
You should try and ask them both at the same time.
My first question is about how does modern physics explain how does the observer influence on the experiment? I mean, the two states of the atom. And the second one is to ask about your impression on how quantum mechanics and quantum physics, being such an intricate subject, influences on the pseudoscientific field and religious. I mean, nowadays we have seen many books and films on the media which tries to explain quantum physics and quantum mechanics not in a scientific basis.
Okay, so to answer the first question about about atoms, when you look at them, or quantum objects, when you look at them, why do they make up their mind? The reason is information has to come from the atom to me in order for me to see it. If I see a hydrogen atom emitting red light, or if I see a sodium atom emitting yellow light, then a photon has to leave the atom and come to me. And as soon as the photon leaves the atom has got to change its energy state, and during that energy state, it loses some information. So it changes the state, it randomizes a bit, and so just the mere fact that I've gained some information has changed it somehow. And in the example of the Schrodinger's cat paradox, the cat, maybe if you work really, really hard, you can get the cat to be both alive and dead, but then just the atoms of the box disturbing it. And as the speaker in the TED talk that you just saw described, his little diving board gets affected by light, and it gets affected by air, and it gets affected by temperature, and disturbs it so that it makes up its mind which of the two states it wants to be in. So any information that leaves the object will disturb it. And going back to your second question, which was about pseudoscience and how people misuse particularly Heisenberg's uncertainty principle and these kind of things for discussions about consciousness. I suppose that the problem is that people don't really understand it. They don't understand what are the limits of such statements. If I say that as soon as you look at something, you change it, and I'm a quantum physicist and what I'm talking about is Heisenberg's uncertainty principle, then I'm applying that statement to a very specific set of circumstances. And then if you come along and you don't know anything about quantum physics and you say, oh, someone really famous and very smart said, if I look at something, I change it, maybe I can borrow that and I can give myself some credibility if I use that statement in talking about something that is sort of nonsense. If I come and shake your hand, I haven't changed you really. You're still the same person that you were. Nothing has rubbed off from me onto you. But if it suits me to say that it has, and I use Heisenberg as some sort of intellectual backup, it's convenient for me to do so. And I guess it stems from the fact that lots of people fail to understand quantum physics, and therefore they feel entitled to exploit the fact that you don't understand it properly either, and I tell you some nonsense, and hopefully you'll accept it.
That's the reason why science communication is so important in today's age. Any more questions?
I do hear still enemy. Sorry. Well, I actually got two questions as well. First of all, to really understand quantum mechanics, as far as I know, you also have to have a deep understanding of mathematics, right? So
well, I'm not sure if that's really true. So what I just explained to you in my talk is all that I understand about quantum mechanics. You just have to say that you're prepared to accept that things behave like waves. And if you understand, if you have a mental intuitive picture about the way that waves behave, then you can have a mental intuitive picture about what quantum mechanics does for you. Now, mathematics always helps. If I understand the mathematics of waves, I'll be able to predict waves. If I understand the mathematics of kicking footballs, I'll be able to understand footballs better. And the same is true for quantum physics. If you understand the mathematics, you'll be able to predict a bigger variety of experiments.
All right. Well, that pretty much summarizes what I wanted to hear. For the second question, if you think that we are able to get such a high computational power, as you said, with quantum computing, do you think maybe if we use cellular automata or any related technique, we could simulate the entire universe and maybe even get predictions of our own world with that?
I should say that there's nothing that a quantum computer can do that a classical computer can't do. It's just a question of how long it would take to do it. So supposing I want to predict the motion of a drug molecule when it binds to a receptor, okay, depending on how big those two things are, I can actually write a computer program. I know all of the physics in order to be able to do that. I can code it into an ordinary classical computer. The question is, how long will it take the computer to run? And the great thing about a quantum computer is that it can do things in parallel. It can hold two numbers at the same time, and it can do two calculations at the same time, and it multiplies up the more and more quantum bits you have in your quantum register. So it's a question of speed and power.
All right. Thank you.
Okay, we have a Twitter question.
Yes.
Could we bring it up? Any chance? I'll try to remember. It's how to. Is there any way how to program qubits to be in multiple states? And I think that's the question.
Okay, so
I think you can click on it if you find it.
I have to say,
could you please start off with explaining what a qubit is, because I've never been clear on that.
Yes.
So inside a regular computer, you have it holds numbers in the transistors, and each transistor is either on or off, representing a 0 and a 1. And each one of those pieces of information, the zeros and ones, we often call them bits. And you probably have a camera on your phone which has got 5 megabits or something, or 5 megapixels. When you save the photograph on your computer, it's saved in a file that has got 5 million ones and zeros in it. So that's all we mean by bits. And a qubit is just the quantum equivalent. It doesn't have to be 0 or 1. It can be both 0 and 1 at the same time. So a qubit is just a representation of a state, and both states at once. If that's a possibility, then you have a qubit. So that's what a quantum computer is.
Is there any thoughts on how to program control the qubits with multiple states in quantum processors?
Yeah, so how do you write a quantum computer program? That's a really hard thing. Has anybody seen the Imitation Game? It's a film that's come out recently about Alan Turing, who is a completely brilliant mathematician who not only thought of how to make the first quantum computer, but actually started to build it himself as well. And I have to say, at the moment, quantum computer programming is still in the realms of such difficult mathematics that you need to be a really serious mathematics professor to be able to understand it, and to think of programs that will be better than an ordinary computer. Your phone is now so powerful that it's actually quite difficult to think of programs that simple programs that will run faster on a quantum computer than they will on an ordinary classical computer. So Alan Turing did a brilliant job in imagining what you could do with a computer before computers existed, and that's sort of the same situation we are in with quantum computers now. Writing a quantum computer program and figuring out what to do with the qubits is actually a difficult problem, and I don't understand it, frankly.
Oh, we have another question.
But it's nice to have things that we still don't understand, of course. I mean, there's still more research questions to answer.
The line between the known and the unknown.
Yeah.
Yeah, my question's to do with particle wave duality. I guess, just checking my understanding. I guess at the macro level, we're used to things either being matter or energy, and we know that these two things are interchangeable. We can go from matter into energy as we do with on the atomic side. It seems that at the micro level, however, where we talk about particle wave duality, it's as if it hasn't made up its mind yet whether it's energy or it's a particle. And in fact, it's both until such time as it settles on one or the other. Is my understanding of that correct? Is that what when we talk about waves, we're talking about energy? And whether something's an energy, whether it's energy or it's matter. And at that level, it doesn't make sense to talk about it.
So the wave-particle duality is a complicated thing, and that's, I guess, where we all have the stumbling block, and we sort of say, oh, I give up, I can't understand quantum physics, because you don't know which of those two types of physics something will adhere to. And I suppose that the key comes in trying to think of, well, what am I going to look for when I look at the object? And if the property I'm going to look for is a wave-like property, it's an interference property, then the thing that I'm looking for will act like a wave. But if the property I'm going to look for is a particle property, and I'm going to look for how much energy it deposits when it collides with something, then it will act like a particle. I'm not sure if I have good examples of this, but supposing I have a cat in a box, but I don't tell you it's a cat, and I tell you to do some experiments to see what kind of thing it is. And you say, well, okay, the first thing I'm going to do is I'm going to listen to it. You might hear the cat make a purring sound, and you think, well, there's a motorcycle in this box. You might not know that it's a cat, but then maybe you want to say, okay, I'm not going to listen, I'm going to put my hand in the box and touch it, and you might feel it, and you feel something, this feels like a cushion, because it's nice and soft. So it depends on what experiment you do, determines what kind of property you get, and that determines the way that the object appears.
Okay, and sorry, everybody else had two questions, so I'm going to do it. So I guess in relation to that, it seems that a lot of it comes down to properties, in which case we're talking about information. And when we talk about state, we're talking about information. So when we talk about superposition, in our sort of classical world, we're used to something having just one state, so one set of information associated with it. But what you're talking about here with superposition is you can have two sets of information associated with something, and they can be mutually exclusive sometimes. But it sort of modulates in and out of the two.
Well, I suppose the key thing is that they're not mutually exclusive, actually. That's why the quantum information is so powerful, is because a regular transistor, it can be on or it can be off. And if it's off, I know it's definitely not on. But in the quantum world, in order to describe the state, is the thing relaxed or is it excited? Those two things aren't mutually exclusive, and that's why it's more powerful. So yes, which properties we're measuring determine which kind of state, but there's all kinds of variables that tell us the state, and they're not mutually exclusive.
Okay, thanks.
Any more questions? Yes, at the front here.
What's your opinion on D-Wave in America and their quantum computers, which they like to sell?
Yeah, so those of you who have heard of a quantum computer before might have come across the story. There's a company called D-Wave, and they're based in Seattle, and they've sold quantum computers to, I believe, to Google and to Lockheed Martin for many millions of dollars each. And those computers have been made a bit in secret, and D-Wave don't tell you what's actually inside the computer. And the customers have bought the computers because of the fact that quantum computers have been shown theoretically that they can do things like sorting jobs very, very quickly. So that's, of course, what Google does. That's its business, is sorting information and trying to pick out the results of searches. So Google were very interested in quantum computers, and they bought one of these machines. Now the question is, I suppose, how powerful was that computer? How many quantum qubits did it have inside it? And are they all entangled together? And the answer is I can't tell you, because we haven't been shown what's actually inside the computer. And then I suppose the second question might be, has it been shown to do any jobs that are quicker than an ordinary classical computer? And the answer to that question is no. People have been running tests on those computers to see, have they been able to do jobs that are quicker than an ordinary computer? And of course, IBM is a big computer firm. They've been very challenging of this company because they don't want to be a SERP. They don't want you to stop buying IBM computers and everyone buy D-Wave computers. Of course, you wouldn't want to shell out $10 million maybe, but it has not been shown yet that that computer is better than a classical computer. Now, I'm very keen that people don't get the impression that quantum computers are rubbish, even if I say that that computer is not as good as it's cracked up to be. It's just the first one. And so it's doing something. It is doing a computational job. It's just not as fast as as your laptop. But of course, laptops are the result of 70 years worth of computer development from the first vacuum valves and mechanical computers. And quantum computers have only been in existence, even though the very thought of maybe one day we could make a quantum computer was only in the 1980s. So we've got a long way to go before we actually overtake the classical computer technology.
Thank you so much for your question. Any more questions? Okay. Yes.
It's a very non-technical question. Someone tweeted saying if they could be in two places at once, they would just double the amount of Netflix they watch. What would you do?
Yeah, well, since I love to be in the lab and do experiments, but I also like to be on holiday at the beach, relaxing at the same time, I would be able to both work and play.
That's fair enough, guys. Lesson to learn: work and play same time.
Okay, any more questions? Comments, notes,
tweets? Oh, we have another question.
One more question.
How big do we think a quantum computer would have to be, like in physical dimensions? Because you were saying that, or you showed a picture and it used lasers or something like that to stabilize it or to give it the conditions it needed. But currently, how big is this D-Wave computer? You know, how big would one expect it to become?
That's a good question. Actually, I've not actually ever seen the D-Wave computer, and I don't know how big the physical machine is. But I don't imagine it's as big as the first classical computer. The first classical computer, ENIAC, which was built not far from here in the National Physical Laboratory, is actually the size of a whole room. And the D-Wave computer is certainly smaller than that. And the kinds of computer that I'm envisaging, although I used very large laser facilities in order to control it, actually we have a strategy that we'll be able to use computers which are sort of tabletop size, and the actual computer itself will just be a silicon chip as small as a grain of sand. So the computer itself will be an extremely small thing, even though the life support systems all around it might be quite large. So I certainly don't imagine this being a big machine, but on the other hand, it's not going to be anytime soon the kind of thing that you can carry around in your pocket. So quantum computers actually have lots of things that you might be interested in as an ordinary citizen. You might want to be able to send perfectly encrypted messages to your friends. You might not want anybody to read your email, and a quantum computer will give you codes that you can make completely uncrackable messages. So there are good reasons why you would like a quantum computer on your desk, but that's going to be some time, I guess.
Okay, we have time for one more question. So, if anyone has one, yes.
Anyone?
Anyone else? No? Okay,
Sorry?
up to you.
All yours.
Thanks. Yeah, final one then. We talked about things being in a quantum state, and we've talked about things being in a classical state. What is it that flips something over from being in a quantum state into being in a classical state? Is it the act of interacting with something else that causes it to flip?
Well, I suppose that very small things can behave like our everyday understanding of billiard balls and footballs and move around in that same way. And the thing that causes them to move that way is whether or not they are interacting with lots of other things. I suppose the key question is how many things are interacting with it. And that's why, for example, the TED speaker talking about his diving board had to suck out all of the air and make the room lights dark and get the temperature really low, is just to minimize the number of things that were interacting with his diving board. The more things that you have interacting with it, the more likely it is to just behave like a classical diving board and just do one motion at one time. The more things that you have to keep track of, the less quantum it behaves.
Thank you so much.
Thank you very much, Ben.
And please
Pleasure.
thank you all for
Round
your
of
wonderful
applause.
questions. So now we'll have another 30-minute break. Refreshments are outside, so
This time, hot tea and coffee. And
Yay.
please, we'd like to remind you, don't bring food or drinks back into the lecture theatre. Thank
see
you
you
very
in
much.
30 minutes.
Okay, microphone, please. Okay, welcome back, guys, to our third and final session. We are very lucky to have today with us Dr. Andrew Steele, who's going to be talking about science funding.
And other cheerful things like cancer? Oh. Yeah.
No, that might come up.
Yeah.
Just to brighten your day.
So Andrew studied physics at the University of Oxford, where he got his PhD. Then one morning he woke up and decided he wants to do biology instead. So currently he's working as a computational biologist at Cancer Research UK.
One interesting fact among many about Andrew is that in 2012 he won the UK final of FameLab. And he also presents his own shows on YouTube, and he's been presenting TV documentaries lately. He most recently went up in a biplane as part of that. Yes, I am very jealous. Please welcome to the stage Dr. Andrew Steele.
So currently he's working as a computational biologist at Cancer Research UK.
Quantities of money are thrown around in the news, and I have no idea what they mean. For example, did you know that in the UK we spend over £100 billion a year on the NHS? We spend £15 billion on our mobile phones. We even spend £80 million a year on peanuts. But I've got no idea how these numbers fit into the bigger picture. And so I decided to try and bring them down onto a scale that I could understand. And when you do that, the most surprising numbers are those that relate to science. So I want to give you a bit of a tour of the UK sort of national accounts and where scientific research fits into all of that. So a good place to start is with one of those mind-bogglingly enormous numbers. The government spends somewhere in the region of £700 billion every single year on all of our behalves. Now, again, that number just doesn't make any sense to me, so I decided to try and make sense of it by dividing it by the population of the UK. And if you take that number and divide it by the 63 million or so of us who live in the United Kingdom, you get a number that suddenly makes a lot more sense. It's about £11,000 per person per year is spent by the government. And that number is more on the same scale as my salary, or maybe it's about a year's rent, so it's a number that I can sort of begin to access. But where does that £11,000 go? Well, most of the big ticket items are fairly obvious and laudable ways to spend our money. We spend about £4,000 a year on what's called social protection, that's benefits and pensions and that kind of thing. We spend almost £2,000 on healthcare, we spend quite a lot on education, quite a lot on defence, and obviously those are just the really high profile categories. There's also this sort of catch-all other £3,500 for everything from parks to policing that the government also funds. But where does science fit into all of this? Well, it's actually funded by a slightly confusing number of different routes from all across government. And in total, the amount that the UK government spends on research and development is about £160 per person per year. Now, at the moment, I don't really know if that's a lot or a little, because on the one hand, it's less than 1.5% of government spending. It's a really tiny figure. But on the other hand, if I got a £160 tax rebate every year, I could probably buy a cool gadget or something, so maybe it's not such a small amount of money. The real way to try and make sense of this is to look at the individual problems that science is trying to solve. And one place we could start, perhaps, is by looking at health. So imagine that these are 10 average people in the United Kingdom. A slightly morbid way to get a handle on health is to look at what kills us. So cancer kills about a third of us, and yet we spend just £4.30 per person per year on public funded cancer research. Now, if there's a disease that's got a 30% chance of killing me, I'd like to spend more than a £5 a year trying to work out why. And maybe how to stop it doing that? But what's worse is that cancer is by far the best funded condition. Heart disease kills 15% of us, about half as many as cancer. We spend just £1.30 per person per year on public funded heart disease research, and stroke kills 10% of people. We spend 28 pence a year researching it. Now, not to be patronising, but this is a picture of 28 pence. This, if you live in the UK, is your entire annual contribution to researching stroke. Now, frankly, that would be slightly rude to leave as a tip in a restaurant, let alone a contribution to a disease that kills 10% of people, possibly including the waiter you just insulted. Now, obviously, science, medical research isn't all about preventing death. What's really important as well is quality of life, and that's much harder to quantify. But one way to try and get a handle on that is to perhaps look at the economic cost of diseases. And a really interesting disease from that point of view is dementia, because dementia is something that affects a lot of older people, but it doesn't very often kill you. A lot more people die with dementia than of dementia. And because you therefore have to be looked after for a number of years, it's a very expensive disease. In fact, the direct health and social care costs of dementia are about £160 per person per year in the UK. And that's stuff like looking after people on the NHS, giving them drugs and that sort of thing. Then there are the indirect costs of the disease, which are much larger than these direct costs. That's things like people giving up work to look after elderly relatives and that kind of stuff. When you add up all these indirect effects that dementia has on the economy, that's another £200 per person per year. So you can combine those. The combined effect of dementia on the economy is £360 per person per year. I'd like to emphasise this is literally everyone, every single one of us in this room, everyone in the whole UK, not just dementia sufferers. And we can contrast that with how much we spend on dementia research. It's that little green line there. It's 60 pence per person per year is spent researching Alzheimer's and related conditions. We can do a similar kind of analysis for the other three diseases that I mentioned, cancer, stroke and heart disease. And that whole massive rectangle comes to about £800 a year. We spend £7 per person per year researching all of these diseases combined. So that's less than 1% of the amount they cost the economy. So even if there weren't a huge human imperative to try and spend more on disease research, there's a massive economic one as well. And this is a problem that recurs across science. The amount that we spend on scientific research is dwarfed by the size of the problems that science is trying to solve. So, as well as health, another thing that's very expensive is energy. We spend about £2,200 per person per year on energy in the UK. That's literally everything: petrol, heating, lighting, factories, shops, the works. And if you add all those things up and divide them by 63 million, you get about £2,200 each. So obviously that's a pretty big chunk of your salary, for example. But also there's an environmental imperative to do something about energy, because most of the ways that we generate it are very bad for the environment. We release carbon dioxide, which is causing dangerous climate change, and other kinds of pollution, which are, again, bad for our health or bad for the environment. So there's another strong reason why we should be investing in energy research. So against this huge economic and environmental challenge, we're spending somewhere in the region of £10 per person per year on energy research. Now, as a recovering ex-physicist, I've got a soft spot for one particular technology, and that's called nuclear fusion. Nuclear fusion is a potentially transformative power source. It's the source of energy that powers the sun. It's kept it burning for 5 billion years. It's going to keep it burning for the next 5 billion. And the way that it works is that you smash hydrogen atoms together, and when they come together at high enough speed, they fuse into helium, and in the process release a huge quantity of energy. What's even better is, as well as powering the sun, there's plenty of fuel down here on the surface of the Earth as well. We think there's about 10 million years worth of fusion fuel on the Earth's surface, if you consider using energy at the rate our civilization currently does. Even better than that, it doesn't release any carbon dioxide, and even though it's got nuclear in the name, there's no long-lived radioactive waste. So this really would completely transform the way humanity generated its power. The problem is, if you know anything about the sun, you probably know it's very hot. And that is the chief challenge with fusion. To get those hydrogen nuclei to stick together, you have to raise them up to hundreds of millions of degrees, and that's a massive engineering challenge. It's an engineering challenge that we've been working on for quite some time now, and in fact, that's the biggest problem with fusion. When you mention it to people, they normally say one of three things. Hasn't that been 30 years away for the last 30 years? Hasn't that been 50 years away for the last 50 years? Or hasn't that been 30 years away for the last 50 years? Now, cynics. If the world could be powered by the jaded aphorisms of cynical smartasses, we'd all be laughing, metaphorically at least. But I think this betrays a fundamental misunderstanding of the way that science works. No amount of time spent not looking for a cure for cancer is going to find one, and similarly, if we continue to underinvest in fusion research, it's going to take us a long time to crack it. I think it makes more sense to think of fusion not as being a certain number of years away, but as being a certain investment, a certain number of nerd hours away from fruition. So, luckily, we have got a plan. The scientists who are working on fusion think it's going to cost us about 60 billion quid to go from where we are now, the experimental reactors, to actually putting watts on power grids of electricity. Now, that sounds like a lot of money, but actually, when you think about it, there might be quite a lot of people interested in near-infinite clean energy. Say, at least the population of the developed world, so we can divide that £60 billion by the 1.1 billion people who live in what are called the high-income countries. That's basically the rich part of the world, the people who could afford to pay for this stuff. And when you do that sum, it comes out as £50 per person. Now, I'd put my 50 quid on the table right now for this utterly transformative power source. And in fact, we wouldn't even need to do that, because it's going to take time to build the labs, do the experiments, train the scientists. And so we could scrape together this 50 quid over a number of years. And suddenly, when looked at through this lens, I think that fusion seems an awful lot closer. So that's health and energy, and it's very easy to make a compelling case for spending more on health and energy research, because there's a very definite, obvious social impact of the research that you're doing. The consequences are very clear and very positive. But what about basic science, blue skies research? Research that's just pure curiosity, we don't know where it's going to lead. Well, an example that people often give when you talk about this kind of science with no particular aim in mind is space exploration. And you might have noticed that recently humanity touched down on the surface of a comet. Now, this is a hugely important space mission. From a sort of basic science point of view, this comet lander is going to teach us about the origins of the solar system and maybe the origins of life. From a sort of technological spin-offs point of view, doing these audacious feats of space engineering mean that regular engineering tends to inherit new bits of technology that are developed from it. And finally, there's the vitally important inspirational value. This thing was just cool. And if we want to inspire future generations of scientists and engineers, we need these kind of big, high-profile projects that are going to be on the news all over the world in order to make that happen. But nonetheless, you might still be scratching your head. Those benefits are all quite hand-waving. How much does it cost to land on a comet? Well, it's quite easy. If you go on the internet, you can find out the number. It's about 1.4 billion euros to create this Rosetta mission, send it into space, and touch it down on the surface of Comet 67P Churyumov-Gerasimenko. Now, that again sounds like an incredibly large amount of money, but it's really important to put these figures in context. So let's try and give it an engineering context first. What can you buy with 1.4 billion euros? Well, it's about the same as the price of 4.2 Airbus A380 aircraft. And the A380 is a pretty cool bit of engineering, but it's not going to get you into space. And I think another thing that's important to mention is these are production airliners. This is something that's being manufactured continuously, whereas the Rosetta probe was a bespoke robotic spacecraft. So, you know, the first Airbus A380 would have cost much more than a few $100 million. And so you can see that actually the Rosetta probe in this context doesn't seem like such bad value. And to bring it down onto my favourite scale per person, you can then divide the amount that we spent on Rosetta by the number of people who paid for it. And actually it comes out as about €3.50 per European. That's because it was launched by ESA, the European Space Agency, which is a massive collaboration of countries. Most of Europe's involved. And so if you divide that 1.4 billion by the number of people who paid for it, it comes out as around €3.50. So that was to land a spacecraft on the surface of a comet. You can compare that to the €8.50 it would have cost you to go and see a load of actors flying a computer-generated spaceship into a computer-generated wormhole had you gone to see Interstellar. And that's based on the average UK cinema ticket price. If you go to one of the swankier cinemas in London, I think you could probably pay €20, and that's before you bought any snacks. This is absolutely incredible that we can send a spaceship to the surface of another world in our solar system for a price that's comparable to that of a cinema ticket. And I think looked at on this scale, again, Rosetta seems incredible value. And actually, you can make it seem even better value than that because this project took place over about 20 years. The design, the build, the launch, waiting for it to travel through the solar system, obtaining and analysing the results. And if you do that division, it turns out the Rosetta mission cost us in Europe somewhere in the region of 20 euro cents per person per year, which is incredibly cheap for this thing that's advancing the bounds of human exploration and human knowledge. So that's a lot of numbers that I've tried to bring down onto an intelligible scale, make them small and try and make them understandable. Let's look at some really big picture stuff, some parts of the global economy and see where huge scientific projects fit into that. One thing that's often cited as a very expensive scientific endeavour is the LHC, the Large Hadron Collider. That's this massive 27-kilometre long tunnel under Geneva where we discovered the Higgs boson. And for this £2.6 billion, it sounds quite expensive, we got 27 kilometres of tunnel in which we can accelerate protons, subatomic particles, to 99.999999% the speed of light. Let's try and think of something to compare that to. Say Crossrail. That's a new train project being built across London. For that, we're going to get, it's going to cost £15 billion, and for that we get 21 kilometres of tunnel in which we accelerate trains to 0.00001% the speed of light. So if you compare fairly mediocre bits of public infrastructure to science, suddenly the science looks incredibly cheap. I also mentioned fusion. It's going to cost us about 60 billion, we think, to get from where we are now to actually putting electricity on grids. Let's compare that to the amount of revenue that Apple made on the iPhone between 2007 and 2012. So this figure isn't even up to date. 123 billion pounds was made by Apple. And bad news, iPhone owners, over half of that was profit. So what that means is that Apple could single-handedly have developed nuclear fusion using the profits from just a single product line. Instead, they developed a big iPhone, a smaller big iPhone, and most recently, a big small iPhone with a fingerprint reader. Actually, come to think of it, it's probably a good thing they didn't invest their R&D budget in fusion and create the iTokamak fusion reactor, because if they had, you could only get the electricity out if you had a special custom-made expensive cable. And even then, only if you had an iTunes account. Nonetheless, you can see that the amounts of money that are being thrown around in commerce dwarf the amounts of money we need to make transformative scientific advances. And here's another scary number. This is the total amount of money we spent on health research all around the world between 1981 and 2010. So it's about 30 years of global public-funded health research, about £600 billion. We can compare that to the cost of the war in Iraq, just to the United States of America, which was £1.8 trillion. Now, whatever your political views on the motivations behind that war and so on, I think it's pretty clear that 90 years of health research, which is effectively what that could have funded, would have been more beneficial to humankind than that particular war. So that's some huge numbers to boggle the mind. What is 1.8 trillion even pounds? Let's go back to those everyday figures that I've been trying to ground us all in for the rest of the talk. These are some of the figures I've mentioned so far, the energy, cancer, stroke, heart disease spends, all in pounds per person per year. And since we've talked quite a bit about health, let's compare that to the amount that we spend here in the UK on alcohol. It's actually about £600 per person per year, and that's literally every man, woman and child, so you've got to hope some of them aren't drinking. Now, I don't want a world where there's no alcohol, but there's another 5 times as much science. That would be a pretty dull place to live. But equally, if I was a space alien, and I touched down on the surface of planet Earth, and I was trying to work out what it was about this strange species I'd found myself amongst, I might log on to the Office of National Statistics website. Now, the first thing I'd think is, my God, this species has got a lot to learn about web design. But if I did eventually find the document I was looking for, I would see that these guys spend £600 a year each on booze, and £5 a year on a disease that kills a third of them. These kind of numbers just don't make any sense. Something else that doesn't make any sense, weddings. We spend £160 per person per year in the UK getting married, which, if you're being observant, is about the entire amount that we spend on scientific research. And finally, loo roll. We spend £17 per person per year on toilet paper in the UK. Now, again, I don't want a world where there's no toilet paper but a little bit more science. I value having a clean bum. But equally, I'm sure I'm not 100% efficient with my toilet paper. I think I could probably cut back by 10% if I really tried, and that would give me £1.70 a year to play with. I could use that to double what we spend on heart disease research. I could use it to septuple the amount we spend researching stroke. And these numbers are just ridiculous, and I think once this slide starts to look a little bit less ridiculous, we're finally getting somewhere with science funding. So that was the Scienceogram. I hope I've managed to put all those ridiculous figures into context, boil them down to pounds per person per year, and for you made sense of science spending. If you want to see some more statistics and stuff like this, then visit the website on scienceogram.org or follow us on Twitter. Thank you.
Thank you so much, Andrew. That was really very enlightening.
Any questions? Same as before, raise your hand.
Or tweet us.
Or tweet us. Hashtag TEDx Surrey University.
We already have a question.
Who has the third mic?
Wait,
No.
You want to play Pass the Mic?
Hiya.
Hey.
You spoke a lot about where funding for science goes, but who's actually responsible for funding science? Is it the government? Is it us? Is it rich people? Who's responsible?
So all the money that I've talked about today has been public funding of science. That's funding that's allocated by the government through a variety of different and extremely labyrinthine and tedious mechanisms. But basically, it's taxes that are collected and then redispersed by the government. There's also a huge contribution from charity in the UK, actually. So health research in the UK is about half of it is paid for by charity funders, which I haven't had time to go into. And I think it's a bit more of a complicated problem because I think government spending is the sort of thing where we can actually increase it wholesale on demand, whereas charity funding is much a sort of organic thing. But yeah, so a lot of health research particularly is funded by charity, but most of the money comes from the government. Another good reason to try and not concentrate on charity, there are two other good reasons not to concentrate on charity, one of which is that the UK is a massive outlier when it comes to charity research funding. We're very, very generous as a nation. Only the US is comparably generous to us, and then the rest of the world is sort of trailing behind for some reason. And finally, I think if you're an organometallic chemist, you're going to have a lot more trouble raising money for charity than someone who's working on cancer, for example.
Any more questions?
Any more questions?
Yeah, what can we do about it?
What can we do about it? Good question. I think the most important thing to do is raise awareness, frankly, because everyone I've spoken to, be they scientists or policymakers, have been surprised by these numbers. It's putting them on this scale suddenly makes them accessible in a way that they simply aren't. When we talk about the 4.6 billion ring-fenced science budget, which is a big thing in politics at the moment, that doesn't really generate the same amount of understanding as dividing these numbers up. And so the most important thing is definitely to raise awareness. If you want to do that, then I think we need to particularly start making MPs and policymakers aware of this. And so if you visit sciencegram.org, hopefully in the next couple of weeks, actually, we're going to be putting up some resources which you can then go and shake at your MP and that sort of thing, and say, look, these numbers are as they are. Most MPs, there's only one MP who's actually worked as a scientist in Parliament. There are a few that have got science PhDs or science backgrounds, but scientists are vastly underrepresented, and so this isn't an issue that people realise is a big deal. It's not something that's necessarily on MPs' radars. And so I think if we can demonstrate there is a sort of groundswell of support and an understanding that science really does need to be funded, then there's a huge potential for change here, because no political party is opposed to science funding. It's just I think it's not recognised as something that people care about. And I think numbers like this and making them more widely accessible is the way to make people care about it.
Thank you for the question. Any more questions? Okay, we have 2 more questions, so we'll pass the mic.
So, with the ALS Ice Bucket Challenge, so much money was raised, but it was only really raised due to sort of fashion and sort of almost peer pressure from other friends. But how do you feel about that? Do you feel like that's beneficial to funding, the research, or or do you think that that was, if anything, detrimental because it was just because of fashion and peer pressure that so much money was raised? I mean, what do you think about that?
I think it's great that these fundraising initiatives have traction. I think it shows, to some extent, as well as there being the peer pressure element, people do care about particularly health research, because there was also the no makeup selfie trend earlier in the year that Cancer Research UK made quite a lot of money off the back of, which was bizarre because they didn't even start it. It was sort of a viral social media thing, which then a number of cancer charities got involved with. And I think these initiatives are great, but the trouble is the amounts of money they raise, they sound big, but they're actually very small. So the ALS Ice Bucket Challenge in the UK raised somewhere in the region of, I think it was less than £10 million. And that sounds like a lot of money, and the ALS Association, obviously that's a huge boost to their annual budget. But when you consider that a lot of the work they do is actually not research either, it's looking after people with ALS, by the time you boiled it all down, it was pence per person had been added to the ALS research budget. And so, although these things generate a lot of media coverage and they're very high profile, I think that, as you say, they're very one-off and sort of quite sporadic. They're not a reliable way to fund science. So I think they're sort of they demonstrate an underlying desire by the public to get involved, particularly with health research, but we haven't really got, they haven't got the power to change the funding landscape in the way that we need. They're not going to transform any of these numbers.
Next question.
So how do you think we should actually get more money for science? Do you think cuts need to be made in government spending, or increase in taxes, or more private investment? Or
I think there's a twofold answer to this. The first of which is it's kind of not our problem as advocates for science, because that's a political question. I think making the case for science spending is very important, and we can say, look, this is vitally important stuff. It needs funding, and it has a demonstrable economic payback as well. So there are a lot of studies that show that the amount of money invested in public science has a huge, huge payback to the economy. There was a study done actually in partnership with CRUK earlier this year about the public return on health research particularly. And they looked at cancer research over the last, I think it was 30 or 50 years. And reliably, it has about a 20 pence return every year when you invest £1. So that's absolutely, blows most other kinds of public or private investment out of the water. But I think, secondly, in sort of more general public finances terms, you've got a very narrow debate in the media at the moment. There's this obsession with reducing deficit down to nothing, as though that's in some way economically significant. But actually, it's quite economically illiterate to talk in that way, because the deficit is just an arbitrary number, and it depends on the position in the economic cycle and all kinds of things that it's very hard to get a measure of. So actually, even increasing government borrowing wouldn't necessarily be a bad thing. So if you're a private company and you saw something that had a 20% return, and you could borrow at an interest rate that's effectively negative, which is what the government can do at the moment because interest rates are below inflation for government bonds, then it's an absolute no-brainer that you should invest more in science, even from a cold economic point of view. And that's before you consider the human ramifications of improving, health and energy research and that kind of thing.
Thank you for your question. Oh, we have one more question.
Thanks. So if we're so generous as a nation, do you think that maybe the problem why there's so little funding coming from the government would be that we've become too dependent on other people's? I mean, I don't know how the rest of Europe does it, but if they're more stingy when it comes to donating to charity, but they're still competitive in scientific progress, then maybe do you think that the government's a problem? Do you think the fact that we're just relying too much on charitable giving instead of...
I think it would be great if the government had that kind of high-level overview of science spending, and I just don't think they do have it. Which is because what's really bizarre about this, watching this talk, you probably think, oh, all those numbers have come out of government reports. Actually, almost none of them have. So astoundingly, all those numbers about health research were done by an independent academic study, which was done on behalf of dementia charity, trying to explain how little we fund dementia compared to its economic cost. The government do not have figures on how much we spend on cancer research in the UK, which is just astounding. And that means that they can't sit back and go, oh, look, it's okay, cancer's being funded 300 million by the government, 300 million by Cancer Research UK, therefore, we don't need to invest so much in cancer research because charity's picking up the slack. The government just doesn't know. And that is the kind of argument you can imagine them having when they're setting these budgets, saying, oh, we don't need to invest quite so much in health research because the UK charity system is a very strong ecosystem. But I really think there's just a total lack of understanding and recognition because the figures simply aren't there. And so I think another sort of aspect of how we can go about raising the political profile of this is just to convince the government to collect statistics, because they've got, they know how big the science budget is, they know how big government departments' research budgets are, but in terms of actual meaningful categories where that money actually goes, there's very little data collection done. And I think that collecting it and then displaying it in a way that we can actually engage with is a huge part of this problem.
Yeah, thank you.
Would you think that the demand for fast track results for science for like a cure for cancer for like 2 years, and obviously that wouldn't happen, do you think that might be a bit detrimental in terms of getting science funding because you couldn't guarantee that, and there's this culture that we need results fast straight away?
I think so. So there's this really poisonous tendency to think of scientific results as being a number of years away. I think it's so important to remember that they are a certain investment away and a certain amount of time away. And often that amount of time is indeterminate because you don't know how long it's going to take to get a certain research result, you don't know how long it's going to take to convert that result into something that you can actually use. And I think another real problem in terms of short-termism is the life cycle of parliaments. Even now with our fixed-term 5-year parliaments, that's still so much shorter than the life cycle of a scientific innovation making it onto the mass market. So, yeah, I think there's a real problem with short-termism, and there's a real problem with quantifying these things solely in terms of economic output as well.
Any more questions?
Yes. I think, okay, so.
Cheers. Back to what you were saying about statistics. I seem to remember reading somewhere that the government's going to start publishing data to the electorate to let them know the breakdown of government spending. Is there therefore an opportunity here to raise awareness if you can start improving those stats and get down to sort of a level of granularity that you were setting out there?
Yeah, I think that's very much the case. So some of you might have received, in fact, in the last month, something called a personal tax summary, which is a government breakdown of how much you've paid in income tax and national insurance, and then how that's allocated through the different government departments. It's a pie chart that's sort of a bit more detailed than that first flow chart I showed you of government spending on my first slide. I think this has real strengths and weaknesses, and I think there's a real problem that it's often used as a political tool. So one of the big sort of hoo-has in the media about this particular breakdown was the welfare category, which is the biggest item of government spending on this pie chart. But actually, because the government are so keen, we could say it looks like the government are keen to demonise whatever welfare is, because when I say welfare, I think a lot of people think, oh, that's people who are unemployed, they're sort of scrounging benefits. But actually, there are all kinds of bizarre things included in that welfare category. For example, nurses' pensions were included in the welfare category, even though the salaries of those nurses when they were in employment was obviously in the healthcare category of spending. And so that's a completely incoherent way to make that distinction. And it's partly because government administration is incredibly complicated. Maybe these kinds of oversights get made, but there were a suspicious number of additional categories in that. But I think what this shows is that it is important to break down the figures in a meaningful way, and the word welfare can mean so many things to so many people, be they government statisticians or members of the public. And so I think it's right that, by making these things more transparent, you can definitely improve public engagement with them and raise awareness of these issues.
Cheers.
Okay, we had another question.
So I have a question about nuclear energy. So in public opinion, I guess, there are issues with the cost and safety of nuclear fission. Do you think that when nuclear fusion gets cracked, that it will face the same issues?
I think it's difficult to say, and it's very much dependent on how it's sold, because when you talk about nuclear energy, the fission variety, the thing most people commonly say back to you is, oh yeah, I remember back in the 50s they were saying it was going to be too cheap to meter. And I think that actually comes down to a single person's quote in a newspaper, which wasn't even a widely held view. But there are these tiny things that can massively influence the way that these things are perceived publicly. And I think one of the big issues is perhaps even the use of the word nuclear. which will just automatically spark fears that you get sometimes things like Greenpeace coming out against fusion, which doesn't make any sense because there isn't any long-lived radioactive waste from the process. So yeah, I think it's going to be interesting to see how it comes out. But on paper, there's nothing to be worried about because you can't have a meltdown in a fusion reactor. If the fusion reactor breaks or there's some kind of technical difficulty, then what happens is within a fraction of a second, all that energy is just dissipated and it's gone. There's literally, you have a fusion reactor the size of this room, there are grams of gas in there. So there's no serious quantity of dangerous material, there's no long-lived radioactive waste, there's no carbon dioxide. So as long as it's sold correctly, there's no reason for people to be nervous of it. But the risk is that pseudoscientists and certain elements of the media might spin it in such a way as it could be misinterpreted. So got to be careful.
Depends on scientific literacy as well.
Yeah, it does.
If scientists do their job well and start communicating more and more, it might not be a problem.
Do you want this back?
Okay, anyone have any other questions? Comments?
Come on.
Bit of a competition.
Yes.
No one?
No?
I have a question. How did you start Scienceogram? What was your initial idea? Why did you start it?
So this is a slightly bizarre story because you might assume I'm a scientist. I have always been a scientist. So maybe I'm just some kind of science groupie who wanted to demonstrate how cheap science was. And perhaps there are other areas of government spending you could apply this to. Now, I'd say that's probably still the case. There might be something I've not seen where you can apply a similar kind of analysis and look at how ridiculously small the numbers are. But this actually started as a project looking at the whole of government spending, doing very much what you were saying the government is now trying to do, looking at breaking down the amount that we spend per person per year. And what you find is, as I showed you in the first slide very quickly, there are a few little interesting stories, but by and large, we spend a lot on health, we spend a lot on defence, we spend a lot on education. There aren't any major stories in there. But what we found when we did this analysis, when we broke all this stuff down, was that the big scandal was science. And so this started as a project looking at all government spending, but I rapidly realised that actually the really interesting story to be told was just about these numbers about science. So we sort of expanded on that, and that's how Scienceogram was born. So it's really frustrating because when you've only got 15 minutes, you obviously can't really give the sort of depth and the background, and people just assume that I'm some kind of science advocate, which obviously I am, but it wasn't conceived as that. This anger in me about science funding is entirely evidence-based.
Thank you. Any more questions? There we go, this side. Finally. Okay, pass the mic.
Excuse me.
Thank you very much for your talk. You said you're doing biology, so that confused me, but you studied physics. Did you have to study biology and then go to the biology? Or what was going on?
I would say I am studying biology right now.
Okay.
The learning curve has been quite steep. I was the reason that I moved, which is again something I'd talk about if I had more time, is actually because I was fascinated by the aging process. So all those diseases that we mentioned, cancer, heart disease, stroke, dementia, these are all diseases that are primarily diseases of old age. Your risk factors for getting one of those diseases or from dying from them rapidly increases exponentially as you get older. In fact, one of my favourite but most morbid statistics is that your chance of dying actually doubles every 8 years you succeed in being alive. So right now, I'm almost 30. My odds of dying this year are somewhere in the region of 1 in 1,700, and I quite like those odds. But if I make it through the next 50 years and I get to the age of 80, then suddenly my chances of dying skyrocket. They're 1 in 20 every year, so you're sort of running this gauntlet. They've gone up by a factor of almost 100. And I guess the physicist in me says, there must be some underlying pattern that means your susceptibility to getting these diseases. There's some process that means that they're all correlated. They all sort of kick in. When you reach 60 or 65, suddenly you start to suffer from more than one of these pathologies at once. And there's good experimental evidence to suggest that there is indeed some kind of orchestration going on. There's some smaller set of processes that governs this susceptibility to disease. And so by trying to understand that, I hope that we can come up with treatments that could potentially prevent multiple age-related diseases simultaneously. And that's something that's dramatically underfunded because it's not a specific disease category. It's not something people have heard of. And so I think it's vitally important we get the word out about that as well.
Great, thank you.
Any more questions?
Any physicists wanting to move to biology?
Any more questions? No? Okay. Well, let's wait for that.
I think the question was, which areas of science do you think the money should go into more?
I think the first message of the talk in terms of which area of science we should invest in is that the most important way to do it is by using a methodology like this. Break the numbers down into pounds per person per year, then compare them in lots of different ways to the different magnitudes of the problems. So for example, as well as science being absolutely underfunded, in the sense that we don't spend enough on health research as a whole, you can also see quite clearly that it's relatively underfunded in that cancer gets a lot more money per death than stroke does, for example. And the same is true within cancer. Different types of cancer, some are relatively underfunded compared to the amount of deaths that they cause. So I think by looking at it all in this way, you can really start to get an idea. And given that, I actually think ageing is a very good example because it covers this huge breadth of economic and social consequences. You know, it's by far the largest cause of human suffering in the world, and therefore we should be investing more money in it. And similarly, I think nuclear fusion is another really good example because it's got such enormous potential, and yet it would cost about the same as the HS2 train line, we think. And that's, you know, albeit an important piece of infrastructure, the ramifications of it are far less than of developing a working fusion reactor. So I think those are two particularly good cases, but by and large, the methodology is to divide it up into pounds per person per year and start doing some meaningful comparisons, and then which areas of science are most important to invest in should sort of drop out from that.
One more question over there.
I'll just shout out. So do you think that the reason why the government doesn't allocate more funding towards it is partly to blame because the scientists not stepping up and actually claiming it?
I think as a community, science definitely needs to get more vocal, yeah. I think the problem that we have for a lot of from a political perspective is that MPs don't feel their seats are riding on science, apart from in a very small number of cases where someone's got a huge national lab in their constituency or something like that, then science doesn't necessarily register. There's a handful of MPs in Parliament who really care passionately about science and campaign on it, but by and large, it's not a big issue. And I think it's sort of a massive chicken and egg situation, that the media don't really care about it, the public don't necessarily care about it as much as they should. And it's partly a realisation thing. I think that it's not obvious how much science does permeate your everyday life, and it's not obvious just how crucially all our healthcare depends on the research that we do. And so there's a lot of people clamouring for increased funding for the NHS or better governance for the NHS, but you don't have that same noise being made about health research, even though everything the NHS does ultimately is based on the research that scientists have done. So I think it's a question of, yeah, scientists definitely need to get more vocal about this, and I think perhaps as a profession, we enjoy being in labs, working out cool stuff, but actually it's really, really important that the public, politicians, policymakers, the whole world is aware of just how much the work that we do can potentially underpin changes in the way that we live.
Thank you very much. And that was the last question, apparently. So thank you very much, Andrew.
Thank you.
And now this has brought us to the last video of today's event. But before that, we'd like to invite on stage TEDx Surrey's president, Jessie Joseph, who'd like to say a few final words. Thank you.
Afternoon, everyone. How are you all doing? That was a bit... What? How are you all doing? Great stuff. Everyone is still awake. That's good to know. Well, it's been a good busy few weeks getting to this point, and right now I just don't really know what to say. My mind is just too blank. But what I will say is a big thank you to everyone who's come here today, and to these following people who have really helped us to put this event together and present it to you guys so well. So the Students' Union of this university, who have helped us with the ticketing, promoting, StagTV, who've been brilliant at filming and setting up the live stream. So guys, thank you very much. Stage crew who set up the lights, the stage, and been really the backbone of this event. Hospitality and catering services who've been providing all the refreshments for us, sponsoring us for that, so thank you very much. And Alumni Fund, very important, who have given us the resources to do this event. So if there are members in the audience who are alumni, or if you're watching this on live stream, I really thank you for your generous contributions. Apart from all those people, who I would also like to thank is my team. About 10-15 of us, they're there around in the audience somewhere. We've all been working very hard for this for the past 8 weeks, and it's been quite a journey, but we've pulled it through, and I hope that you think we've done you justice for this event. I'm not going to talk for too long because we have a brilliant video coming up, And I think the video kind of summarizes the whole point of doing this science event. It brings in everything from funding to, being really brave enough to go out there in the science world and just go after what your heart says and just going after what you want. So I'm going to leave it to the video to sum it all up for you. And yeah, that's it. Thanks, guys.
We live in difficult and challenging economic times, of course, and one of the first victims of difficult economic times, I think, is public spending of any kind, but certainly in the firing line at the moment is public spending for science, and particularly curiosity-led science and exploration. So I want to try and convince you in about 15 minutes that that's a ridiculous and ludicrous thing to do. But I think to set the scene, I want to show, the next slide is not my attempt to show the worst TED slide in the history of TED. It is a bit of a mess. But actually it's not my fault, it's from the Guardian newspaper. It's actually a beautiful demonstration of how much science costs, because if I'm going to make the case for continuing to spend on curiosity-driven science and exploration, I should tell you how much it costs. So this is a game called Spot the Science Budget. This is the UK government spend. You see there it's about 620 billion a year. The science budget is actually, if you look to your left, there's a purple set of blobs and then a yellow set of blobs. And it's one of the yellow set of blobs around the big yellow blob. It's about £3.3 billion per year out of 620 billion. That funds everything in the UK, from medical research, space exploration, where I work at CERN in Geneva, particle physics engineering, even arts and humanities are funded from the science budget, which is at 3.3 billion, that little tiny yellow blob around the orange blob at the top left of the screen. So that's what we're arguing about. That percentage, by the way, is about the same in the US and Germany and France. R&D in total in the economy is something like publicly funded, is about 0.6% of GDP. So that's what we're arguing about. The first thing I want to say, and this is straight from Wonders of the Solar System, is that our exploration of the solar system and the universe has shown us that it is indescribably beautiful. This is a picture that actually was sent back by the Cassini space probe around Saturn after we'd finished filming Wonders of the Solar System, so it isn't in the series. It's of the moon Enceladus. So that big sweeping white sphere in the corner is Saturn, which is actually in the background of the picture. And that crescent there is the moon Enceladus, which is about as big as the British Isles. It's about 500 kilometres in diameter, so a tiny moon. What's fascinating and beautiful, this is an unprocessed picture, by the way, I should say. It's black and white, straight from Saturnian orbit. What's beautiful is you can probably see on the limb there some faint sort of wisps of almost smoke rising up from the limb. This is how we visualise that in Wonders of the Solar System. It's a beautiful graphic. What we found out were that those faint wisps are actually fountains of ice rising up from the surface of this tiny moon. Now that's fascinating and beautiful in itself, but we think that the mechanism for powering those fountains requires there to be lakes of liquid water beneath the surface of this moon. And what's important about that is that on our planet, on Earth, wherever we find liquid water, we find life. So to find strong evidence of liquid, pools of liquid beneath the surface of a moon, 750 million miles away from the Earth, is really quite astounding. So what we're saying essentially is maybe that's a habitat for life in the solar system. Well, let me just say, that was a graphic. I just want to show this picture. That's one more picture of Enceladus. This is when Cassini flew beneath Enceladus, so it made a very low pass, just a few hundred kilometres above the surface. And so this again, a real picture of the ice fountains rising up into space. Absolutely beautiful. But that's not the prime candidate for life in the solar system. That's probably this place, which is a moon of Jupiter, Europa. And again, we had to fly to the Jovian system to get any sense that this moon, as most moons, was anything other than a dead ball of rock. It's actually an ice moon. So what you're looking at is the surface of the moon Europa, which is a thick sheet of ice, probably 100 kilometres thick. But by measuring the way that Europa interacts with the magnetic field of Jupiter, and looking at how those cracks in the ice that you can see down on that graphic move around, we've inferred very strongly that there's an ocean of liquid surrounding the entire surface of Europa. So below the ice, there's an ocean of liquid around the whole moon. It could be hundreds of kilometres deep, we think. We think it's salt water. And that would mean that there's more water on that moon of Jupiter than there is in all the oceans of the Earth combined. So that place, a little moon around Jupiter, is probably the prime candidate for finding life on a moon or a body outside the Earth that we know of. Tremendous and beautiful discovery. Our exploration of the solar system has taught us that the solar system is beautiful. It may also have pointed the way to answering one of the most profound questions that you can possibly ask, which is that are we alone in the universe? Is there any other use to exploration and science other than just a sense of wonder? Well, there is. This is a very famous picture taken actually on my first Christmas Eve, December 24th, 1968, when I was about, 8 months old. It was taken by Apollo 8 as it went around the back of the moon, Earthrise from Apollo 8. A famous picture, many people have said it's the picture that saved 1968, which was a turbulent year, the student riots in Paris, the height of the Vietnam War. The reason many people think that about this picture, and Al Gore has said it many times actually on the stage at TED, is that this picture arguably was the beginning of the environmental movement, because for the first time we saw our world not as a solid, immovable, kind of indestructible place, but as a very small, fragile-looking world just hanging against the blackness of space. What's also not often said about the space exploration, about the Apollo program, is the economic contribution it made. I mean, whilst you can make arguments that it was wonderful and a tremendous achievement and delivered pictures like this, it cost a lot, didn't it? Well, actually, many studies have been done about the economic effectiveness, the economic impact of Apollo. The biggest one was in 1975 by Chase Econometrics, and it showed that for every $1 spent on Apollo, 14 came back into the US economy. So the Apollo program paid for itself in inspiration, in engineering, achievement, and I think in inspiring young scientists and engineers 14 times over. So exploration can pay for itself. What about scientific discovery? What about driving innovation? Well, it looks like a picture of virtually nothing, and what it is a picture of the spectrum of hydrogen. See, back in the 1880s, 1890s, many scientists, many observers looked at the light given off from atoms, and they saw strange pictures like this. What you're seeing when you put it through a prism is that you heat hydrogen up and it doesn't just glow like a white light. It just emits light at particular colours, a red one, a light blue one, some dark blue ones. Now that led to an understanding of atomic structure, because the way that's explained is that atoms are a single nucleus with electrons going around them, and the electrons can only be in particular places, and when they jump up to the next place they can be and fall back down again, they emit light of particular colours. And so the fact that atoms, when you heat them up, only emit light of very specific colours was one of the key drivers that led to the development of the quantum theory, the theory of the structure of atoms. I just wanted to show this picture because this is remarkable. This is actually a picture of the spectrum of the sun. And now this is a picture of atoms in the sun's atmosphere absorbing light. And again, they only absorb light of particular colours when electrons jump up and fall down, jump up and fall down. But look at the number of black lines in that spectrum. And the element helium was discovered just by staring at the light from the sun, because some of those black lines were found that corresponded to no known element. And that's why helium is called helium. It's called Helios. Helios from the sun. Now, that sounds esoteric, and indeed it was an esoteric pursuit, but the quantum theory quickly led to an understanding of the behaviours of electrons in materials, like silicon, for example. The way that silicon behaves, the fact that you can build transistors, is a purely quantum phenomenon. So without that curiosity-driven understanding of the structure of atoms, which led to this rather esoteric theory, quantum mechanics, then we wouldn't have transistors, we wouldn't have silicon chips, we wouldn't have pretty much the basis of our modern economy. There's one more, I think, wonderful twist to that tale. In The Wonders of the Solar System, we kept emphasising the laws of physics are universal. It's one of the most incredible things about the physics and the understanding of nature that you get on Earth is you can transport it not only to the planets but to the most distant stars and galaxies. And one of the astonishing predictions of quantum mechanics, just by looking at the structure of atoms, the same theory that describes transistors, is that there can be no stars in the universe that have reached the end of their life that are bigger than, quite specifically, 1.4 times the mass of the Sun. That's a limit imposed on the mass of stars. You could work it out on a piece of paper in the laboratory, get a telescope, swing it to the sky, and you find that there are no dead stars bigger than 1.4 times the mass of the Sun. That's quite an incredible prediction. What happens when you have a star that's right on the edge of that mass? Well, this is a picture of it. This is a picture of a galaxy, a common or garden galaxy with, 100 billion stars like our Sun in it. It's just one of billions of galaxies in the universe. There are a billion stars in the galactic core, which is why it's shining out so brightly. This is about 50 million light years away, so one of our neighbouring galaxies. But that bright star there is actually one of the stars in the galaxy. Right? So that star is also 50 million light years away. It's part of that galaxy, and it's shining as brightly as the centre of the galaxy with a billion suns in it. That's a type 1a supernova explosion. Now that's an incredible phenomenon because it's a star that sits there. It's called a carbon-oxygen dwarf. It sits there about, let's say, 1.3 times the mass of the Sun, and it has a binary companion that goes around it. So a big star, a big ball of gas. And what it does is it sucks gas off its companion star until it gets to this limit called the Chandrasekhar limit. And then it explodes. And it explodes and it shines as brightly as a billion suns for about 2 weeks and releases not only energy but a huge amount of chemical elements into the universe. In fact, that one is a carbon-oxygen dwarf. Now, there was no carbon and oxygen in the universe at the Big Bang, and there was no carbon and oxygen in the universe throughout the first generation of stars. It was made in stars like that, locked away and then returned to the universe in explosions like that in order to recondense into planets, stars, new solar systems, and indeed people like us. I think that's a remarkable demonstration of the power and beauty and universality of the laws of physics, because we understand that process because we understand the structure of atoms here on Earth. This is a beautiful quote that I found. We're talking about serendipity there, from Alexander Fleming. When I woke up just after dawn on September 28, 1928, I certainly didn't plan to revolutionise all medicine by discovering the world's first antibiotic. Now, the explorers of the world of the atom did not intend to invent the transistor, and they certainly didn't intend to describe the mechanics of supernova explosions, which eventually told us where the building blocks of life were synthesised in the universe. So I think science can be, the serendipity is important, it can be beautiful, it can reveal quite astonishing things. It can also, I think, finally reveal the most profound ideas to us about our place in the universe and really the value of our home planet. This is a spectacular picture of our home planet. Now, it doesn't look like our home planet, it looks like Saturn, because of course it is. It was taken by the Cassini space probe. But it's a famous picture not because of the beauty and majesty of Saturn's rings, but actually because of a tiny, faint blob just hanging underneath one of the rings. And if I blow it up there, you see it. It looks like a moon, but in fact it's a picture of Earth. It was a picture of Earth captured in that frame of Saturn. That's our planet from 750 million miles away. I think the Earth has got a strange property that the further away you get from it, the more beautiful it seems. But that is not the most distant or most famous picture of our planet. It was taken by this thing, which is called the Voyager spacecraft. And that's a picture of me in front of it for scale. Voyager is a tiny machine. It's currently 10 billion miles away from Earth, transmitting with that dish with a power of 20 watts, and we're still in contact with it. But it visited Jupiter, Saturn, Uranus and Neptune. And after it had visited all 4 of those planets, Carl Sagan, who's one of my great heroes, had the wonderful idea of turning Voyager around and taking a picture of every planet it had visited. And it took this picture of Earth. And it's very hard to see the Earth there. It's called the pale blue dot picture, but Earth is suspended in that red shaft of light. That's Earth from 4 billion miles away. And I'd like to read you what Sagan wrote about it, just to finish, because I cannot say words as beautiful as this to describe what he saw in that picture that he had taken. He said, "Consider again that dot, That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives. The aggregates of joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. It's been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Beautiful words about the power of science and exploration. The argument has always been made, and it will always be made, that we know enough about the universe. You could have made it in the 1920s, you wouldn't have had penicillin. You could have made it in the 1890s, you wouldn't have had the transistor. And it's made today, in these difficult economic times. Surely we know enough, we don't need to discover anything else about our universe. Let me leave the last words to someone who's rapidly becoming a hero of mine, Humphrey Davy, who did his science at the turn of the 19th century. He was clearly under assault all the time. We know enough at the turn of the 19th century. Just exploit it, just build things. He said this, he said, nothing is more fatal to the progress of the human mind than to presume that our views of science are ultimate, that our triumphs are complete, that there are no mysteries in nature, and that there are no new worlds to conquer. Thank you.
Everyone, thank you very much for coming today. I hope you really enjoyed your time. Can I just ask one last thing of all of you? If you could please leave us some feedback, either by email or Facebook or Twitter, anything, it's completely fine. Just so if you've enjoyed the event, just so we know for ourselves, and then just tell everyone that TEDx Surrey University is great. We are trying to organize another event for March, so please do keep an eye out for the details of that event. Would be good, so yeah. Also, because we just never sleep, we're also doing a collaboration event on Monday, 15th December, because this week is Human Rights Week. It's called Being Human, Being Free. Tickets are on sale on Tix2. That's going to be, again, brilliant, from 6 to 9 o'clock in Rubik's. So if you're free, please do come along. That's set to be another amazing event. So yeah, thank you very much, and goodbye.